Okay, we are now recording. Let's get the slideshow set up from the current slide. And we're on page 415, measuring time. All right, any questions on anything so far? Okay, yeah.
I noticed that the test was very different than what was shown in Blackboard.
Oh, really?
Yeah.
Which is that?
Test two.
Test 2? Let's see.
I noticed it was different than what was Blackboard.
Oh, really?
I didn't know if you was right.
Maybe I entered that incorrectly. No. Ah, I see what I did. Well, no, I don't see what I did. I think I do know what I did. I see yours for a second. That's good. Yeah, sorry. I don't know how I did this, but you were right next to each other in the book, and I put your score under her and her score under yours. So let me make sure I get this right. Okay. I'll get those changed next time I'm in Blackboard, which maybe this afternoon I'm going to try. I've got a big thing that I've got to get done this afternoon. But if I can get, what's that? That's the correct score, but I had it wrong in my book, and I took it out of my book to put it on Blackboard. So, yeah. Okay. Good deals. Glad you caught that. You're not, though. Okay. It wasn't much difference. Okay. All right. Any other questions? So let's talk about what we're going to do today. We're going to continue in chapter 16, and I think we'll get most of the chapter done. In fact, I think we'll get the whole chapter done. What I don't know is how much time we're going to have for the lab. But I think I mentioned to you before, this lab is going to require observations at night or morning, whenever you want to observe, over a 2-week period. And it may not be able to start yet, depending on what time you want to make your observations. So, this lab we won't do totally. We're going to do a lot of it in class, but part of it you have to do at home. Okay, you're going to be observing the moon. So, with that in mind, we probably, if we do finish the chapter today, which I think we will, then we'll start on the lab. If we don't get finished with the lab, we'll finish the lab next time at the very beginning, and then move on to chapter 17. That okay? Sound okay? All right. Let's see how far we can get in today. And then also, depending on when we get that done, I will try to call, and that's another thing I've got to do this afternoon, Channel 13 Stanford University, to see if I can arrange a visit. Because y'all did want to go to the planetarium, right? Yeah, that's what I understood. And I just want to see if he wants to do it for 4 people. I think he will. He's a really nice guy. But if you have friends, acquaintances, and stuff like that, now, if they're students, okay, would y'all be able to get to Stanford yourselves? I mean, with 4 people, I think I could almost carry everybody in my vehicle, but especially if you'd be going home after the visit there, would you want to take your own vehicle, or would you want transportation? Just let me know, because I need to plan for that as well. You would drive, okay. Huh? You would, okay. Well then, I'm sure I could get the other 2 if they don't have transportation. So I will. Now, if you are inviting anyone else, that's why I brought the transportation up. They wouldn't be able to participate in school transportation, but if we're getting there ourselves, you can bring anyone you want. I'm pretty sure it's okay with Mr. Weigel at the planetarium. If I were taking the school vehicle, we can only take students. So, but any other students would be able to. But if you're, if we're going to do private vehicles, you can bring anyone you want. I'll check with Mr. Weigel on that. Okay. And also, if he says, when I call him today, well, the Thursday's the only day I've got, then we'll plan to go on Thursday. I'll have to get it out to you on Blackboard. So please check Blackboard announcements today and tomorrow and Thursday before class to see if we're going or not. All right. Any questions? How are we going to proceed? All right. Now, we've talked a lot about this before, but we're going to continue it. We measure times. Time standards depend on measuring the intervals between evenly spaced periodic events. Okay? Now, if you remember from the last lab, the analemma, sometimes noon was before clock time, sometimes it was after clock time, and that could differ from close to 30 minutes. Okay, remember, could go plus 16 or minus 16 or 14 or something like that. So yeah, there's a big thing. Well, that's not quite good enough. We need to have evenly spaced periodic events. So, we base on the rotation of the Earth and its axis. Of course, that's what makes a day. Revolution of the Earth around the Sun, that's what makes a year. So that's the basis for the day. I asked you this before, what's the basis for month? The moon. Yeah, the moon's rotation around the Earth. And the seasons, what characterizes that? Combination of two things. Not this. Say again? What about the sun? Okay, that's part of it, okay? Part of seasons is that we, the Earth, are moving around the sun, okay? What's the other part of that? Do we move like this? If we move like this around the sun, there wouldn't be any seasons. Equatorial area always hot, poles always cold. Everybody has 12-hour daylight, 12-hour darkness. Does that happen? Tilt of the Earth, exactly. That, how many degrees? 23.5 degrees. That's exactly. Because of that tilt we have, and the fact we're going around the sun, gives us the seasons. Right now, where are we? We're tilted just about as much toward the sun as we can. Because what's tomorrow? Say again? Summer solstice, exactly. Sun will be the very highest in the sky all year long in the northern hemisphere. Lowest in the sky all year long in the southern hemisphere. But for us, it's our summer solstice. Then, in the fall, we'll be here. In the winter, we'll be tilted away from the sun as much as possible. And then next spring, we'll be back here again. So it'll be even. Okay? So, the astronomical examples, the rotation of the Earth gives us day. Revolution of the moon around the Earth gives us month, approximately. The tilt and our revolution around gives us season. And of course, the revolution around the sun gives us year. Now, there are different ways to measure days, months, and years. We may not use the sun. What if we decided to use a star? Okay? Be legitimate. Sun's a star. Why not use another star? Well, we'll talk about this in lab. We'll talk about it here too. And let me not get into it until we get the slides up. Okay? Let's first start with daily time. Daily time, basically, the rotation of the Earth, is the primary thing giving us our daily time. If you viewed above the North Pole, the Earth rotates counterclockwise around the sun. So I was just doing it backwards. It wasn't. I don't like this. Oh no, it says revolves counterclockwise. Viewed from above, no, I was doing it right. Okay, this would be counterclockwise. Looking from down, at us, this would be counterclockwise, and that's how I thought I was doing it right. Okay, around the sun and rotates in the same direction. Okay, so we're rotating counterclockwise, looking down from the north, and revolving around the sun counterclockwise. Why didn't we make clocks go the other way? I mean, if we had, everything would be the same. Okay. However, on Earth, that makes the sun appear to rise in the east because we're turning. Let's get our globe out here. Viewed from above, we're rotating counterclockwise. Yeah. Okay. And so you see, right here, you're going to be the sun for us today. You're very bright. Okay. So right here, I just see you coming up over the horizon. If I'm here in Birmingham, just see you coming over the horizon. This. Okay. And then at noon, you're right overhead, highest thing, and then you set in the west. Okay? So that's what it looks like from Earth. Okay? Except that's not all. Okay? Because not only are we spinning, which should give us a day, but we're also very slowly move about 1 degree. So that adds a little bit to our day because we're moving this direction as well as spinning in this direction. So say at noon, right there today, when we spin one time, we have to spin just a little more to be noon tomorrow. Because we move 1 degree this way, had to spin just a little bit more to get our noon. So that's what's happening here. We spin one revolution, but one revolution has, say at noon this day, we're looking right toward the sun. One revolution later, we'd be looking right this way. We have to go just a little bit more to get a local noon. So, because we've moved 1 degree along the revolution around the sun. That's a little exaggerated, but you get the general point. Okay? Now, remember I said, what if we had chosen a star, not the sun, to be our reference for a day? That star out there at midnight, when it reaches its maximum height, it would be right here. The next day, that's right where that star is. Our turning doesn't make any difference to the star because we're not revolving around the star, we're revolving around the sun. It's only our spin that makes a difference there. So therefore, the day according to stars is different from a day according to moon. That periodic rotation, periodic event, you see, back here, we said the astronomical, time standards depend on measuring intervals between evenly spaced periodic events. If we're basing it on the sun, then we have to add a little bit of time for our extra rotation. If we're basing on the star, nope, one rotation is it. And we don't have to add any more. So that's why we really do have two different types of days. Solar day based on the sun and one based on the star is called a sidereal day. Okay? Strange word, and they don't put it on this slide. Well, there we go. Now, let's look at the sun's motion across the sky. Noon is the time at which the sun is on our celestial meridian. Today it was almost as high as it's going to be on that. Tomorrow it'll be just a little higher, and the next day back to about what it was today. Okay? The time at which the sun crosses the celestial meridian, that is our apparent local noon. When I was in the Navy, we called it local apparent noon. Okay? LAN. Well, I think they use LAN for something else. Now they call it apparent local noon. But whatever, you got the general idea. At your particular longitude. But you see here in Bessemer, that would be a little different than Birmingham or Tuscaloosa because we're at different meridian. Okay? So if we went by this, everybody would have a different clock. Everyone along one meridian would have the same time. Another meridian would have another time. We don't do it that way. Okay? Now, the apparent local solar time is given by the position of the sun in the sky. Now, that's never off too far from what real is, but it is a little bit. And that's what they used to do when they used the gnomon or the sundial. Okay? And there is a picture of this in your text, figure 1619, and we actually have one in our garden. Not much of a garden, but it's just a little, it's cheapy, but it's there on the ground. I always try to get it facing the right direction, but the dog and others kick it, and it never is right, but that's okay. We don't use it anyway. That's not the time shown on clocks. Okay? A couple of reasons for that. Remember, we go different speeds around the sun because of that figure 8, remember? And sometimes we're ahead, sometimes we're behind. What is that figure 8 called again? Second? Okay, that's one word for it, but the one that they use in the lab. Analemma, exactly. Okay. So, because the Earth has all these weird things, we go at different speeds, our tilt is different. Look at this. 100% attendance today. Way to go, team. Y'all are, I think, the best class I perhaps ever have had about being here every day, everybody. So that's fantastic. First day there were only 3 here, but ever since then, we've had everyone here, I think. And because of that, I'll give you a reward. Here is your first lap. That's how to go and recover. So I think that's your page 2, isn't it? Yeah. Okay. And what's even more, I'm so excited about it, I can give you your first test. Okay. I can't give you your second lab, though. So you still have it. Okay. You don't have to do it now. But I can give you your second test while everybody's heard that. There you are. But whenever you want to turn in the second lab, we'll take it. Okay. Now, what I was just saying before is our days aren't always the same length. You know, the noon doesn't always cross at noon, you know, before, after clock time, and things like this because of Earth's tilt, the rotation around the sun, the sun's ecliptic where it is relative to the celestial equator, all those things, you know, those deviations. We saw the analemma. Okay? So therefore what we do, we average the time from apparent solar time. Okay? If the noon to noon, actual local apparent noon, is 1 day, 23 minutes, and 23 hours and 53 minutes, and the next day it's 23 hours and 50 minutes, and sometime later it's 24 hours and 2 minutes. And what we do is average all those solar times over the entire year, and it averages over two effects. And we mentioned this: the Earth's orbital speed changes throughout the elliptical orbit. Coming up in July, when we're right about here, where are we relative to the sun? Close or far? We're as far from the sun as we'll ever be. So that means we're moving more slowly than we ever do, okay, because we're further from it. And then over in January, just past Brian back there, where are we relative to the sun? Closest we'll ever be. Not by a lot, but a little bit. So we're moving the fastest we ever do. So that changes our average day. So the Earth's orbital speed changes throughout the elliptical orbit. And the other fact is that the equator is inclined toward the inclined to the elliptic. Celestial equator, this way, I think it's this way right now, and the ecliptic is that way right now. In fact, this is the largest deviation we have will be tomorrow, 23.5 degrees. So our mean solar day, that doesn't mean mean solar day, but average solar day is a 24-hour average from the mean solar time. Okay. So that's where we get our 24-hour day. So what are these possible days? One is the length of time required for the Earth to rotate once about its axis. That's not a solar day. That's a sidereal day, because one turn around the axis has stars being at the same place. It doesn't have the sun at the same place. The interval between two consecutive crossings of the celestial meridian by some particular star out there, say at midnight or some other time of the night, that would be the sidereal day. That would be one spin every time. Little variation because of the Earth's constant rotational rate. Now, is it really constant? No, we are slowing down, but ever so slowly. You're not going to notice a difference in hundreds of years, but we are slowly slowing down, okay? So that's why the sidereal days have no variation in them. They're always the same. However, our apparent solar day, solar is dependent on what? Old Sol. Who is Sol? Sun. Sidereal, I don't know, that must mean stars, okay? Now, later we'll see there are other names for stars, okay? The interval between two consecutive crossings of the celestial meridian by the sun, and the problem with that is our revolution around the sun changes the Earth-Sun orientation every day, okay? So we are a little bit further. It's about 4 minutes longer than the sidereal day, okay? Now that means this should be over here, okay? This last tick should be here, not there. The apparent solar day is about 24 hours. The apparent sidereal day is 23 hours, 56 minutes, and 4 seconds long. This should be over here because we've already know the solar day, mean solar day is about 24 hours. Okay? The other is 4 minutes. Sidereal day is 4 minutes shorter. The solar day is 4 minutes longer, because we travel around the sun as well as spinning. Does that make sense? Yay or nay? All right. Now, another name for that analemma is the equation of time. So you can go by either that you remember better, equation of time or analemma. This traces the yearly variations between apparent local noon, I keep wanting to call it local apparent noon, apparent local time and the mean solar time. This appears as that good old figure 8 on the floor. And I told you before we could actually draw it if we wanted to. Every day that we had good sun, we'd probably have to cut down the maple tree out there. It just doesn't let the sun come in enough. But if we blocked out all the light except one little hole in the window, and then exactly when the sun crosses our meridian every day, whatever time that was, plus or minus, we marked on the floor that spot that the sun would form. We would form a figure 8. If we did it over the entire year, we would get it. The two effects, the axis tilt, okay, that certainly comes into play. That means the sun appears to go north of the celestial horizon, like it is now, celestial equator, and in the winter it will go south of it. So that's the north-south motion along that equation of time, figure 8. Other name for it? Analemma, exactly. The other thing that makes a difference is the orbital speed. Like I said, right now we're getting close to it, as far from the sun as we'll ever be. So that means we're a little bit slower than what we'll be next January when we're the closest and fastest. Okay? And that orbital speed accounts for the east-west deviations. And that equation of time is the cumulative of all this. Okay? And that equation of time is sometimes, well, this indicates the axis tilt. In the summertime, the sun is up here. In the wintertime, it's down here. This basically shows the ecliptic of the sun, on the globe over time, and that makes it look like that. Because June 21st, or somewhere right around there, the sun is directly overhead where? The dotted line right here. Tropic of Cancer. And the sun is directly over the equator where? When? No, directly above the equator. Not July 21st. Say again? March and September. Okay, or somewhere thereabout. March, September, June. Okay? And when is it down here? As low as it will go in the northern hemisphere, as high as it will go in the southern hemisphere? Is what? Yeah, December 21st. And where is it directly overhead then? Tropic of Capricorn. You can read well. No, I'm just kidding. Okay. Exactly. Okay. Now this is a little bit better. Okay, not quite where we are, but this shows when the clock time is before the sun, is shown by the sundial, but that's also an analemma, and this is when it's behind, ahead, or before, behind, before. Now, take this, fold it right there, and what do you have? Figure 8, the analemma. Okay, it's also called the equation of time. Okay. And you could actually call it a sundial, but it's not quite like we. You see, this gets almost 15 minutes before the sun here, and down here, almost 15 minutes behind the sun. I think in the actual one we saw in our lab last time, it actually got up to 16 on one of those occasions. Any questions? All right. Now, that also necessitates that if we've got a 360 degrees around the Earth, right? Sphere, circle, right? At any time, let's say right now, let me pick this up here. We're just ever so slightly before noon. Before time would you say it was over here in the Marshall Islands? The sun's just coming out this morning. What about over here in Madras, India? It's midnight. And how about over here in Mauritania? Is second? No. Evening, yeah, the sun's just going down. Okay? So you see we're at different times across around the globe, around the earth. And since there's 24 hours, and every one of those hours, somebody's at one of those times, 360 degrees, that means there's 15 degrees for every hour of a time zone. And rather than everybody using their local apparent noon, which would be different for every meridian, we decided within that 15 degree block we'll all be about on the same time. Not quite. It's adjusted for local consistency. And let me show you what they mean by that. Okay. These aren't exact, but they're approximately true. These are about 15-minute intervals, 15 degrees circles here. But you see, that would cut off part of Maine and put it out on the Atlantic time. Maine doesn't want to be part on the Atlantic time and part Eastern time with the rest of us, so Maine has elected to all be in Eastern Standard Time. Okay, this one coming down from Canada here that separates Eastern from Central. Well, Michigan all wanted to be on the same time, so all of the state of Michigan is, but Wisconsin, majority of it was on this time. They wanted to all be together, so even though part of Michigan is just right there next to Wisconsin, they're an hour different. I mean, this place is further west than this place here, and yet they are an hour ahead. Okay? So Michigan could all stay on. Now, Indiana got a little crazy. And I'll tell you approximately why. I don't know this for absolute certainty. But does anyone know what's right here in this corner of Michigan?
I think some of that is part of the Chicago metro area.
Okay, that's Illinois. And yeah, that's, okay, you got it. This is the Chicago metro area, and they wanted all of that to be on the same time zone. So people don't have to get up on one time zone and drive in and be at a different time zone. So they did that. And believe it or not, there is a place in Alabama that does it too that doesn't show up here. Does anyone know where that is? Yeah. I think it's somewhere near Opelika. But it's right on the border. You know, the Chattahoochee River, I think down there is the border between Georgia and Alabama. And right across from Columbus, Georgia, a lot of people from Alabama work in Columbus because they got Fort Bragg. It's a pretty good sized city. So those folks, even though it's maybe not official, they go on Eastern time, okay? Because they work on Eastern time, so they live on Eastern time. Now, poor old Florida covers so much here, and these places down here are more associated here, so they cut off. This part of Florida is central, that part of Florida is eastern. Same thing over here. Texas is all in the central, except for this little wedge here. And why is that? Right across here is Santa Fe, New Mexico. And these people associate more with that than they do. There is no nearest town in Texas. You have to go a long way to get a major city, where Santa Fe is right there. So they go with that. Same thing here. Can't think what the southern part of Colorado, whether that's Boulder or Aspen or something down here. The people from Kansas head this way rather than going way across here to get their big purchases. Same thing with Nebraska. Over here, these folks go to Denver rather than going back to Lincoln and Omaha. Okay, so they just go on back. And North Dakota, South Dakota, same thing. It's just where they're comfortable. Part of Oregon is actually Mountain Time, even though it should be Pacific Time. because it's closer to the larger cities here. You got a huge mountain range here. The Rockies, I guess, is here, or Sierra Nevadas or something, and they just don't go this way. They go that way, okay? But these up here, they go to Washington, okay? So yeah, it's adjusted for local consistency, okay? Fortunately, except for that little bit near Georgia, Fort Benning, Georgia, or Columbus, Georgia, Alabama's all central time. Now, daylight savings time, don't even get me started on it. This is a construct, in my mind, okay, in my mind, is so the bankers can golf late in the day in the summertime. They want to get in early. I mean, the sun comes up, let's go and get in early so we get off early and have extra hours of golf. Now, they say they blame it on the farmers. You know, the farmers don't care. We had a neighbor who was a dairy farmer. Guess what? Those cows need to be milked. They don't care about daylight saving time. Twice a day, every day, about the same time every day. It's not the farmers, I don't think. What were you going to say?
Well, I learned back in grade school that was because of the railroads.
The railroads?
Yeah.
Okay, those executives like to play golf too, don't they?
Yeah.
No, I'm just kidding.
If you're going to catch a train from, let's say, Georgia to Texas.
Right.
They had to have a standard time.
Right. Yeah.
That's what he did.
Okay. Maybe that's it too. I think it's the golfers, but I don't know. It's whatever. But the clocks are set ahead in the spring, and we say spring ahead and fall back. Yes.
I've heard also like energy consumption.
Okay.
I've heard that too, just it lessens energy consumption.
Okay, and that has a little more credibility. Okay, and so that may be more modern reason why. Now, what makes no sense to me when you talk about energy consumption is what we do with our school systems. We start classes in August, which is just about the hottest part of the year. Why in the world don't we, we used to start in September, and yeah, midterm came in the middle of January. That's okay. But no, they didn't want to do that. They end now in May, which is still fairly cool. In fact, even June is not bad, okay? But starting in August, so some of the things they claim they do for energy consumption makes no sense. I don't know if they even claim that, but I think it's just to get midterm to be before Christmas, and then after Christmas you start the new term. So they had to move it. But energy-wise, that makes no sense at all to start in August and end in May. We should shift a little bit, and that's what we used to do too. Okay, but yeah, that may be right for daylight savings time. Now, one problem with this though, and we talked about this last time too. Over here in the Pacific is this line that happens to be exactly opposite the zero meridian. What do we call the zero meridian? Another name for it. Prime meridian. Okay, the prime meridian that goes through what place in England? Greenwich, England is where the Naval Observatory is in England. Just a little bit east of London, I believe it is. And that's where the zero meridian is. Okay? Unfortunately, directly opposite that, we have another line which is called the International Dateline. And the thing with that is, if you're, okay, let's see if I can get this set up.
You lose a day going west and you gain a day going.
Just like you do with hours. Yes, exactly. Because right here, you're the sun. Oh, let's see. Our other suns come back. One of you are sitting in between. That desk in between is the sun, right? Okay? And when it's directly overhead here in Birmingham, Alabama, Bessemer, Alabama, okay, the sun is just beginning to rise on the international dateline. Okay? But on one side of the international dateline, I'm sorry, it's here. On one side of the international dateline, it's today, which is the 20th. And the sun's just coming up on the 20th there, but just past there, the It's the 21st, okay? Sun's just coming up on the 21st because you got 24 hours in between, so one side is a day ahead of the other. You're absolutely right. Now, the international dateline is the 180-degree meridian. It's designated to correlate with the days within the 24-hour time zone. Now, again, there's a few local consistency issues there, and here's what they are. 180 meridian, if you drew it right through here, this part of Siberia would be a day ahead of the rest of Siberia. Well, who cares? Who lives there anyway? No, they want to keep Russia all on the same day anyway. But we do the same thing because here, part of Alaska, there's this island chain that we call the Aleutian Islands. They belong to us. And some of them would be over here on the other side, and they would be a day ahead of the ones over here. So they zigzag the line to go down the Bering Strait, even though that's not the 180 degrees. So Alaska's on one day and Siberia's on the next. All of Alaska, including the Aleutian Islands. Okay? They do the same thing down here. I can't remember which group of islands this is, but they wanted to be on the same day. And New Zealand has a few outskirt islands here. They wanted to be on the same day, so they zigzag a little bit here too. So you do it for local consistency. The rest of it's pretty straight because it's right in the middle of the Pacific, which is a lot of ocean. Who cares? Now, I'll tell you a couple of dumb stories with that. Well, one of them's dumb, the other was reality. But I thought was sort of dumb at the time, still is. When I was in the Navy, the first 3 years I was in the Pacific, and we were going back and forth across the Pacific pretty regularly, okay? The first year it was about every 6 months, and then it turned to be more like every year. So I made, I think, 3 Westpac cruises. And every time when we were going one way, and let's see, is that gaining or losing an hour? Yeah, we were going west, so our days would be a little bit longer because we were going the same direction. So when we would add an extra hour, this was sort of good, they did. In the Navy, they have 4-hour watches. Midnight to 4 in the morning, 4 to 8 in the morning, 8 to 12 in noon, 12 to 4 in the afternoon. But then rather than 4 to 8, and the people on watch wouldn't have a chance to eat supper, okay, or have to wait till either eat at 4 before 4 or wait till after 8. A lot too. They have what they call the dog watch. You split it into 2-hour watches, 4 to 6, 6 to 8. So the people going on watch 6 to 8 can eat early. And the people coming off the 4 to 6 will eat a little bit later. But it's all around 6 o'clock. When we would add an hour, they'd always add it to the dog watch. Okay? So one of them would be a 3-hour. I think that first one. So they could get an extra hour workout out of it. You know, that's what it felt like. Okay. But you know, coming back, the hour we lost every time we crossed the time zone, it was always at midnight. It was always at 12 to 4 in the morning. So everybody got cheated out of an hour's sleep. Everybody hated it, except those people on the mid-watch that only had a 3-hour watch that day. They said, all right, okay, because they would go on at midnight and just 3 hours later be relieved at 4 o'clock. So they did that. Now, when we crossed the international date line, though, when we had to add a day, no, it just always was a Wednesday, it seemed like. Always a Monday through Monday through Friday anyway. So we had a 6-day work week that week. Every time. But when we went back, it was either a Saturday or Sunday we lost. I think it was usually Saturdays. Didn't seem right, okay? But they did it for a week. Okay. Now, here's the dumb story. I don't know if this is true or not, but I've heard it said it was. That somewhere here in the Pacific, there's actually an island that sits squarely on the international date line. I don't know if that's true or not, but they swore it was. There we go. be in the Aleutian chain. I don't think it was, but it could have been. Yeah, it could have been somewhere in the South Pacific too. Yeah, there it is. Venu Levi, or there's several islands that, I mean, basically get smacked right on the international dateline. Supposedly, I don't know if this was true or not, this island and this portion of the island where it crossed the international dateline, someone had the cleverness, I'll say, to build his bar right there on the international dateline, so that when it turned Sunday on one side, the customers just moved to the other side because it was then Monday or Saturday, and vice versa. Okay, whether that really was true or not, but supposedly someone had done that, and so they could always stay open 7 days a week. Didn't have to close on Sunday. Okay, I don't know if that really happened or not, but that was the rumor that they did. Okay, enough on that. Okay, any questions about international dateline, time zones? Oh, and by the way, just for the purpose of time zones, remember they're 15 degrees each hour. Well, we center that. Let's start with the Greenwich Mean Time. We center 0 degrees right in the middle, meaning it goes from approximately 7.5 east to 7.5 west. That's what they do. It's not on the 0 to 15. That's not a time zone. It's centered on these. So centered on that one, centered on this one, centered on that one. Those are your 15 degrees as you go around. So ours, which is the go back a slide, the central time zone should be centered on 90 degrees west, 7.5 degrees either side of that. So that would, trying to picture this on a map, you can't see it, but here is the 90 degrees west. That goes basically almost smack through New Orleans and Jackson, Mississippi, Memphis, Tennessee. St. Louis is awfully close to it. Madison, Wisconsin's really close to it. It goes right there. So actually 7.5 degrees on either side of any of those cities. And certainly Alabama is within that pretty much, okay? Halfway between this one and that one. That pretty much is the Georgia-Alabama line. Awfully close to it. That's probably pretty close to it right there. So 7.5 degrees on one side, 7.5 on the other. But obviously that's not a straight line on the other side. Okay. But that would split North Dakota pretty evenly. In fact, most of North Dakota, I think, would be on the mountain time. But you see, there's nothing out here, so they want to stay, because they probably had east to Minnesota to do their stuff. So they stay there. South Dakota has not much to choose from, so they pretty much in the water. Okay. All right. Any questions on that? Now let's talk about yearly time. Okay, I said it wrong. The stars are always sidereal. The one based on the sun, which is 2 consecutive spring equinoxes, rather than calling it a solar year, they call it a tropical year. Where does that come from? I don't know, except that the equinoxes, that's where the sun crosses the equator, celestial equator, so it's directly overhead on those equinoxes, so it's smack dab in the tropics. Of course, the sun's always in the tropics, okay? So the tropical year is based on, and here's the problem. Do we rotate on our axis axis about 24 hours a day, right? And do we go exactly 365 rotations by the time we get back here? No, we go a little bit further. We're not geared that way. No reason we should be or not, but it's about 365.24220 mean solar days. That's almost a quarter of a day more. So how do we account for that extra quarter of a day? Leap year. Every 4 years, we add a day in February 29th. Actually, I had a friend who was born on February 29th. He had finished college by the time he was 6 years old. I mean, 6th birthday, nothing. Just make that up. Well, 5. Something like that. Okay. So we add, and what are the leap years? Every year that's divisible by 4. What are we now? 2017. Is it a leap year? No. It won't be divisible by 4. 17 is not. Was last year a leap year? Yes, 16 was. 16 divided by 4. 18 won't be. 19 won't be. 20 will be. So if the year is divisible by 4, it's a leap year. With one exception. If the century is divisible by 4, as in the year Y2K, now this has nothing to do with that event, but 2000, because 2020 was divisible by 4, we did not have a leap year that year. Because you see, this isn't quite a quarter. Okay? So about every 400 years, we don't have a leap year. On 2000, y'all lived through that, right? I know I did. Okay, y'all were alive in 2000. All of you? Any of you born since 2000? Okay, so whether you remember it or not, there wasn't a leap year that year. Next time we won't have a leap year, 2400. I'm not going to be here. Okay, I don't think so. Okay. Now, so a tropical year is basically one time around the sun. What would be a sidereal year? Sidereal meaning based on, tropical based on sun, like solar. Sidereal based on stars, okay? The interval between two consecutive alignments of the Earth and the Sun relative to the stars, okay? It's about 20 minutes longer than a tropical year, okay? So we go by the tropical year. That's what all our things are going to do by. This one is your sidereal year. Now, if you notice that, 20 minutes is about a third of an hour, okay? So that would add another 0.33 to that, so it would be 0.57 or something like that. The adjustments to keep the calendar year current with the seasons makes a leap year every 4 years. Now, I've never, before this book, heard of a leap second, okay? Now, I think I heard something similar to it, someone suggesting there was another way to do this, that you wouldn't have that. Just make every second a little bit longer, you know? And so you would have it, but we don't do that, okay? And then the not observing leap year every 400 years, okay? Every century that's divisible by 4, okay? All right. Now monthly time. Okay, wait, time out. Okay. There is a nice little example in the book. How many sidereal days are in 1 year? So you would go back to sidereal days. Here, I forgot to do that. And what is the age of a 20-year-old person in mean solar days and in sidereal days? It's a lot of math. It's sort of fun to go through. So if you don't want to actually do the math, you can follow the math in the book. And then they ask the question the other way, how many sidereal days are in one sidereal year, and the length of the sidereal, blah, blah, blah. Okay. Again, it's sort of like they make up these examples to do, not that anyone really cares. Okay. In the other parts of the book, those are really pertinent examples. These are just sort of fun things they decided to do. Okay. In your text, you'll see the actual analemma like we saw in the last lab. That's on page 418. The top of page 419, Science and Society, it talks about saving time, the daylight saving time. You really don't, but you save, in a sense, daylight hours. You group your daylight hours together a little more coherently, especially in the evenings. Otherwise, if you didn't have it, you'd have a lot of daylight hours in the morning that you're not using, and then in the evening you'd have fewer of them. So why don't go on and start the day earlier when it's still darkish and stuff, or just sort of like, and start it then, and then when you get through, you have lots of daylight left. So you're not really saving any time, you're just redistributing it a bit. Okay? Now, there is an example here, 16.5, how many time zones is Honolulu, Hawaii, and they give you the latitude and longitude. Behind New York City, they give you latitude and longitude. Does the latitude matter at all? No. It's the longitude. So what you do is subtract those from each other, and you see that it's 84 degrees apart. 15 will go into 84, close to 6 times. So it's between 5 and 6. I think it's 6 time zones different. Yes, it is 6 time zones. The next question, how many time zones ahead of Denver, Colorado, is the Bay of Fundy in Nova Scotia? And they give latitude and longitude. Does latitude matter? No, it's only longitude. Take the difference between those two. That looks like about 39. And divide 15 into 39. And you get between 2 and 3. And it happens to be 3 time zones. Because Nova Scotia is in that Atlantic time zone that Maine should be, part of Maine should be, but we kept it in Eastern time zone. Okay. Trying to catch up our page turning here. All right, now we're talking about monthly time. And what does monthly time depend on? Basically, the moon. The moon's revolution around the earth. Okay? Guess what? We have 2 types of months. Sidereal month, what would that be based on? Stars, sidereal stars. And then why don't they call it, well, I guess they wouldn't call it solar, and they wouldn't call it tropical, because it has nothing to do with tropics. So they have a completely new word, the synodic month. Okay? Now, here's the difference of this. If here you are on the earth, and here's you have a full moon. Okay, by the time the moon goes all the way around the earth again, to come back to being a full moon, the earth is moved. Okay, so if this was based on the stars, the moon eclipsing some star way out there, till the next time it eclipses the same star way out there, that would be a sidereal month, which is considerably shorter than the synodic month, which is between one full moon and the next full moon. Because you see, with the earth moving up here, the moon going around the earth, it has to go a little bit further to line up with the sun. So that's what makes the synodic month based on phase of the moon to phase of the moon, full moon to full moon, new moon to new moon, first quarter to first quarter, last quarter to last quarter, whatever it is that you're basing on, it has to be a little bit longer. So the sidereal month will be 27 1/3 days. That's the orbital time of the moon around the Earth with reference to the stars, to the synodic month, which is the time between two consecutive phases of the moon, full moon to full moon, whatever, is 29 1/2 days. Okay? That includes the effects of Earth revolving around the sun while the moon's revolving around the Earth. Okay? So this is not quite 2 days longer. No, a little more than 2 days longer. Now, why in the world our months are then not 29 days and 30 days? I do not know. That would be a good research topic. Why did they come up with 30s and 31s, except for 128? I mean, whoa, where did that come from? Why would they do that? I don't know. Seems like we ought to have every other month a 29-day month and every other month a 30-day month. That would account for 29 1/2 days, wouldn't it? It would come out perfectly. But no. How do we do those? Any of you know how you remember which days have what? Which months have how many days? Well, I remember from the old sort of nursery rhyme. 30 days has September, April, June, and November. All the rest have 31, except for February, which in turn, and it goes into 28 or 29 days, okay? So I can remember that because of the rhyme. But then I saw someone do, this is probably when I was in college or something, make a fist. Look at your knuckles. The big knuckle is going to be the 31 day. So that's January, short months, not 30, but short months, February, March, April, May, June, July. August, so 2 31s in a row, September, October, November, December. So actually January and December are 2 31s in a row. That works pretty nicely. So I can do that and not have to recite a nursery rhyme because it takes me a while to get all the way through it. Okay? So I can do that January, February, March, April, May. Okay. And it does pretty well. Little mnemonic device. That's all it is. Any questions about our monthly time? I had never heard the word synodic month before I started teaching this course out of this book. Nor had I heard a year called a tropical year. Solar, in fact, I don't even think I had heard the term sidereal either before I started teaching this course. But now I'm sort of used to it. Now we move to 16.4, talking about the moon. And I think this is the last section in the chapter. But it's a fairly good-sized section. Okay? The moon, at 380,000 kilometers away from us, that's on average. Again, it's not a perfect circular orbit, it's a little bit elliptical. Okay? And that would be, if you multiply that by 0.6, be about 250,000, 260,000, something like that, miles from the Earth. Okay? Now, the moon is characterized by craters. Why would there be craters on the moon? Say again? Yes, lots of collisions with meteors, right? Why would it have more collisions with meteors than we do? We're bigger. We have just as many collisions. The thing is, we have an atmosphere. It doesn't. Our atmosphere burns up most of those meteors before they ever reach the ground. When they do reach the ground, what do we call them? Meteorites, exactly. On the moon, if one comes in its path, no shooting stars there because nothing's burning up. Crash, crater. Okay, so that's why there's lots of craters. Now, there's what they call the lunar highlands, sort of high areas, and Maria, which are, now that word came from the word for the sea. There's no seas on the moon, as in oceans or anything, but from the earth it looks like there's flat colored areas that look like they could have been water, and they thought they were and called them Maria. Later we found out it's just little areas. These are actually ancient lava flows, and that's why they're a little bit darker in color. Okay? There's no atmosphere on the moon. None. I don't know if you realize, but one of the moon missions, I don't know if it's the first one or a later one, if I were to stand here and have a hammer in this hand and a feather in this hand and release them at the same time, what happens? Describe the motion. Hammer goes straight down and bangs first, the feather weaves around. Ultimately, it'll get down there much slower. Why? Because heavy objects fall faster than light objects. Now, that's what Aristotle said. It's not true. Why? It's because air resistance. And that all depends on the force due to gravity downward, which depends on weight, and the air resistance, which depends on surface area. Feathers have large surface area. One of those missions on the moon, when they actually did a moonwalk, the astronaut went out there and carried a hammer and a feather, released them at the same time, and guess what? They did at the same time. Because there's no air to offer any air resistance on the moon. So they do fall at the same rate. Okay? Galileo was the one who said, nope, Aristotle's wrong. Okay, no atmosphere. Now, the moon was the subject of 12 Apollo missions. Now, there were several more Apollo missions than 12, but those were preparation missions. They were practice runs, you know, as they were testing the equipment and stuff. That's what the other ones, not those 12, okay? Now, which one was sort of the disastrous one? Second? You may have said it right. 13, exactly, the unlucky number, right? They made a movie out of it. Tom Hanks, I think, was in it, and I know the other guy, I can't think of it now, but Opie, y'all remember? Yeah, Ron Howard directed it, and it was a pretty good movie from what I hear. I never saw it. I wish I had. Sounded like it was a great movie. Okay? That was the one they were, had they quite gotten to the moon yet or somewhere close to it or something, and they had a disastrous leak of some nature, and they all had to get into what would have been the lunar landing module and fly that back to Earth. And it was scary. I mean, they came really close to losing it. If they hadn't been for quick reactions and quick thinking, they probably would have been one like the Challenger at Columbia. You know, a big disaster. Okay. This is the picture that's in your text. They've used it for several editions here. Picture of the moon composite taken from several satellite photographs put together. This is one of the poles. I don't know if this is the South Pole or the North Pole. I'm guessing the South. It looks like it would be, of the moon. And let's see if I can get it right. I think the light ones are the lunar highlands, and the darker areas are the Maria. They look like they could be seas or bodies of water in between continents. They're not. They're the ancient lava flows, and these are the highland areas. Okay, so that's basically what your moon looks like. Now, we've gotten many samples of soil from the moon, so they know a lot about its composition, at least near the surface. They've done a lot of measurements there. Actually, nowadays, I don't know why, we have probably got better information about Mars than we have the Moon, because they've had several rovers that have made many trips and stayed on Mars for a very long time, collecting a lot more data. Seems like we should have done that to the Moon too. I think there were a few lunar landers that did around, but we didn't have the technology then that we did later with the.
So why do you think that is?
What's that?
Why do you think that is?
I can't hear.
Why do you think that we're more interested in Mars than the Moon?
Well, part of it is that since we've detected water on Mars, I'm not sure. It seems like they have detected some really deep water on the Moon, but there's always a hope that maybe Mars had life on it. No chance that the Moon ever did, okay, that we can tell. So I think that's part of it. The other thing is, we had to beat the Russians, and we got to the Moon first. We beat them, we smacked them there. They were sending out lots of things to Venus, so we wanted to go to Mars. I don't know. I don't know the reason for it, but any of those could be parts of it.
Conspiracy theorists.
What's that?
Some conspiracy theorists.
Yeah, exactly. Right. Okay. It looks like there's a concept supplied that you can read about. I don't know if I agree completely with that, but we'll leave that alone. Okay. What I'm guessing was the thing that was supposed to go in that space that didn't get there is this table 16.2. This lists the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 Apollo missions that did make it to the Moon or got that far. Notice 2 through 6 you don't see. Anyone want to guess why you don't see 2 through 6? In fact, why Apollo 1 is even mentioned? What do you read about Apollo 1? The what? The crew died. Okay? Now, this was supposed to have been our big break. Before this was the Mercury missions, little bitty spacecraft, one person at a time, this kind of stuff. We were going for the big guns now. Sending up 3 at a time, and being able to, go out of the Earth's orbit. Mercury stayed always in Earth's orbit, didn't, mess with the Moon, didn't get that far. So we were really, I'm sure they spent a lot of money, a lot of effort into perfecting this, and the crew died in their spacecraft during a test 3 weeks before they would have even launched. They were up there in there and, practicing and doing a variety of things there, and I think something caught on fire or something. They died sitting on the ground. Who were those 3 astronauts? Gus Grissom, Ed White, and Roger Chaffee, I think it is. I can probably remember those names better than any, except for Aldrin and I can't remember his name. The ones who actually walked on the Moon the first time. And the reason is my wife's from Huntsville. Her dad worked for NASA. Guess what high school she graduated from? Grissom High School, named after Gus Grissom. Virgil Grissom was really his name. His nickname was Gus. There is a junior high there in town. I'm not sure she went to that. Maybe her sister did. But it's Ed White Junior High. And there's also an elementary school That's called the Chaffee Elementary School, because Huntsville was booming and growing at this time. This was 1967. The space, Huntsville was full of, NASA space and stuff like this. So lots of people felt really, really close to the program. In fact, I bet you a lot of the work had happened there, and they named the next 3 schools that were commissioned after these 3 astronauts. High, junior high, or middle, or whatever you called it, and elementary. That's why you don't see a 2, 3, 4, 5, or 6 listed here. Those, they waited a long time. Look at the long time, several months, and they practiced. They studied to see what went wrong, how they make sure nothing like that happened again. And then after that, you see 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All were active around the moon. Except, of course, for 13. That was the first abort in deep space. The lunar module was used as a lifeboat to return the crew safely to the Earth. A major leak or something happened within the capsule. They had to retreat, get into the module, seal themselves off, and drive it. It's like driving a tricycle coming back when you took a jetliner going out. It was incredible. Okay. The last one there was Apollo-Soyuz. What in the world is that about? The first. What's that?
It launched 2 spacecraft from different countries.
I couldn't hear.
They launched 2 spacecraft from different countries.
Okay, right. First International Space Rendezvous. First time a coordinated launch of 2 spacecraft from different countries. And Soyuz was the Russian or Soviet space station. And, we cooperated with them in that way. All right, good deal. I guess we beat that to death. But that's what I think was in this slide here. Subject to 12 Apollo missions. I think this green box was supposed to be there. Probably they took it out because by the time they shrunk it to there, you wouldn't have been able to read it anyway. Now let's look at composition and features of the moon. Okay? We didn't know this before. We actually walked there to notice it. The surface of the moon is about 3 meters. Now, how much is 3 meters? About the height of the ceiling. Because I'm about 2 meters tall, probably a little less than 2 meters tall, and there's another half of me up there, right? So the height of the ceiling, or maybe a little bit more, a fine gray dust on the surface. So all you've got is a single-story building worth of dust, okay? You could build a whole basement and still be in the dust, okay? Now, why in the world is that there? Remember those craters? What was the reason for that? All those meteors hitting the moon's surface, okay? And when the meteors hit the moon's surface, the big ones crash and they split into, lots of little pieces, breaking off parts of the moon's surface too, pulverizing them into fine dust. But there's lots of micrometeorite. In other words, there's a lot of space dust out there, not just big chunks, but space dust. If it hits the moon, it stays on the moon, okay? Now, some of that dust is actually glass beads, because when those major impacts happen, there's a lot of heat given off. And that actually melts the material, and then it hardens. in spheres or beads. Okay? Now, remember the Maria, which were not seas, but actually lava flows? Those rocks are basalts. What is, well, next chapter we're going to talk about basalts. I'll give you a heads up here. Basalt is a igneous rock, we'll talk about that later. That meant it was molten at one time, meaning melted, liquid, and it hardened into a solid. Okay? That's what it means to be an igneous rock. Igneous fire was once hot enough that it was melted. Molten means melted. Lava means it's on the surface. So basically, what this is meaning, at one time the moon was pretty active volcanically. Okay? In other words, it was spewing out stuff from below the surface. Not happening anymore. We'll talk about this in a later slide. Okay? But it did happen relatively frequently in its early days, and so the molten lava made these basalts, and by the way, basalts are fine grained, meaning they cooled quickly. That means the lava cooled on the surface of the moon rather than deep inside the moon, meaning small crystal size. We'll talk about that next chapter. The lighter colored highland rock were formed about 4 billion years ago. 4 billion years ago. Now let's think back. About how old is the solar system? You remember that? Chapter, the last chapter I think it was. Basically, we think the sun's been around about 5 billion years. We think it has about a 10 billion lifespan, and it's been about half of that. So that means that the Highland rock, we think, was formed about 4 billion years ago. So early in the solar system's foundation, that's when the Highland rock was formed. The darker colored Maria, which is what I was saying before, ranged from 3.1 to 3.8 billion years. That would have been the active volcanic period. Okay? We call that seismic period. 3.1 to 3.8 billion years old. Okay? Now, what would be the internal structure of the moon that would account for some of this? Well, 65 to 130 kilometers of the outer rock are outer rock, and then you have a partly molten iron core. Does that sound familiar? The Earth's core is molten. Okay? We've talked about that a little bit before. We're going to hit it some more in the next chapter. And it's mostly iron. So in other words, the moon structure is not a lot different from ours, except we're much bigger, more molten. They're only partly molten in the core. Yeah, so there's a few differences. Now here's a very interesting thing. The outer rock surface is 65 kilometers thick. That would be about 37, 38 miles thick. Near the Earth. The other side, the far side of the moon, or the book named that, I think, 130 kilometers of outer rock. Okay? And that would be about 80 kilometers thick. 80 miles thick. Okay? Isn't that a bit bizarre? Okay? That closer to the Earth it's thinner, farther away it's thicker. There's something inherent here we're going to talk about a little bit later. Something really bizarre about the moon. Which side of the moon do you see? Is it spinning? Every other object in the solar system is spinning. So yeah, you would think it's spinning. But guess what? It spins so slowly that we only ever see one side of the moon. In other words, one time around the Earth is also one spin of the moon. Starts this way, spins, 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 spins. And it's gone one time around as it went one time around us. Isn't that a bit strange? And the part we see is that where the thinner rock is. The part we don't see is the thicker part. Here is, I'm jumping ahead, but here's the one theory, and they feel pretty good about that this might have happened. Sometime back there, about 4 billion years ago, okay, maybe a little beyond that, early in our solar system history, remember, it was a weird time, lots of things flying around and collisions and stuff. There is a theory something major collided with the Earth and actually broke off part of it. And that part of it broke off, of course, that was so much energy involved, it was molten, and it spun and made into a sphere that is the moon. Because originally it was going, if it was part of us, it was going around. If it broke off, it's still going around that way. Okay? Strange. But that would account for the thick part being outside and the thinner part inside, if that actually was a break. Don't know that for sure, but that's the theory. So here's the history of the moon. Okay? Stage 1, and they sort of have, no they don't. I thought they had a figure that went with this, but they don't. They just have almost the same stages here. The origin stage. This is what the theory is. The moon was formed from material ejected from some really major collision with a very large object with the Earth. Okay? Now, time out and an aside here. Remember what was so weird about Venus? It goes around counterclockwise of the sun, just like Earth and all the other planets do, but it spins clockwise. And it spins really slowly clockwise too. I wouldn't be at all surprised if this, back in the early stage when there was a lot of junk flying around there, Venus might have gotten hit too by something and made to turn backwards. Not very fast, but a little bit. Just an idea. I think Mr. Weigel was the one who said something that made me think that could have happened. I asked him, hey, yeah, I wonder if it did. Okay. So that was way back there, about 4 billion years ago, stage 1. Some big collision happened. When that happened, the surface of the moon from that major collision was so hot, the molten surface was about 100 kilometers deep. That's about 60 miles deep. Okay? What was the inner part of the Earth, of the moon? About 65 kilometers thick. So we think that was probably, I'm sorry. Oh, okay. What I'm going to have to do is look at it. It's in between 65 and 130. Okay, 100 kilometers deep. So the part of it got swung to the outside and part to the inside. Now, the molten surface was about 200 million years after the formation. Okay, 200 million years after the formation. Let's go back here again. What's the difference in 4 billion and 3.8 billion? 200 million. Okay? 200 million. I don't know if those are exact, but they sort of fit pretty well. This molten phase existed for about 200 million years after that huge collision. The heating from the solar system debris impacts. And again, shortly after the solar system was formed, there was lots of junk flying around out there, you know, and lots of impacts, lots of pretty major things. It kept the surface molten because it was just getting bombarded with stuff pretty regularly. Okay? Then what happened is the surface cooled. Okay? And now it's the interior is molten. Accumulated heat from radioactive decay. Hey, guess what radioactive decay is? When the sun was going through its first starting its fusion, blowing up, contracting again, doing all that kind of stuff, a lot of radioactivity going on there. Okay? And over time, the radioactive decay sort of slows down. Now, I believe this is a wrong slide. I think this is 3.8 billion years ago, ended about 3.1 billion years ago. That matches what we saw on the previous slide, right? So I think those are billion years, not million years. And if you look in your book, you'll see those are billions, not millions. So this was a typo from the graphics person. Okay? This should be billion, and that should be billion. Both of those billions. All three of those billions. Okay? So, formed about 4 million years, had the surface molten for about 200 million years, got down to about 3.8 billion years ago, and then to 3.1 billion, the molten surface stage. And that would have been, molten interior stage, that would have been when you had most of your volcanic activity, which is when the Maria was formed, right? The lava flows, volcanic activity because of the molten interior. Well, what has happened since then? The whole body has gotten cold and quiet. For about the last 3.1 billion years of its 4 billion year life, it's not been doing much of it. The surface is scarred with micrometeorites and meteorites, lots of craters. Some of those could be very, very old, like way back when all this stuff was happening. Others of them could be more recent, but they just don't happen as frequently as they did back then. So basically, yeah, we still got some mostly molten stuff in the core, but it's not escaping to the surface. The surface is solid enough that there's no volcanic activity to speak of anymore. Make sense? Now, I'm almost certain, though, they still have moonquakes, like earthquakes. So I think there's still shifting going on there, but it's just nothing that breaks through the surface like volcanoes anymore. They did about 3.1 billion years ago, but no longer. And stage 4 in your book also says billion. Whoever did this was not very careful in their proofreading. Any questions? Now, want to take a break? We've been going at it, about 50 minutes or so. So you want to take a break? What's that? Since he's going, why don't we all just do a... No, wait. Thursday, day after tomorrow. This is Tuesday. Trying to throw me off here, aren't you? That was intentional, I can tell. Okay? We are recording again, by the way, so I call that. Okay. Actually, I said it wrong before. 6.4 was just talking about the moon. 6.5 is the Earth-Moon system. This is the last section in the chapter. Okay? I was thinking it was a long section, but this is the last section. Now, this is something I've said several times before in the last chapter specifically. So here we hit it again, and they put it on the slide this time. Our moon, compared to us as a planet, our little satellite moon, compared to us as a planet, the biggest ratio you've got. The Earth, the moon, is the largest moon relative to the size of this planet. Certainly, Jupiter and Saturn have bigger moons than we do. But those are huge planets, you know. And relative to our side, our Earth to mass, Moon to Earth mass ratio is by far the highest in the solar system. Now, think of it this way too. How many moons does Mercury have? None. How many moons does Venus have? None. We have one, and it looks like it may have been formed by a collision with the Earth. So we probably didn't originally have a moon. Okay? Now Mars has two. They're pretty small and insignificant. But what is Mars right next to? Second, it's next to Earth on the inside. What's on the outside of Mars? Asteroid belt. So it probably picked up a couple of asteroids that got out of orbit and they started going around that. So really it seems like that probably the inner four, the terrestrial planets, maybe started out with no moons. But we don't know that. But because of that, must have been a major collision, major collision, that the Moon to Earth mass ratio, highest in the solar system. The diameter of the moon is about a quarter of that of the Earth. So if the moon's there, we're about 4 times bigger, diameter-wise. Mass, however, only about 1/81st the mass of the Earth. Well, that happens because when you quadruple a diameter, okay, that's what 4 times that would be Earth, then the volume goes up by the cube of that. 4 times 4 times 4 would be 64. So that, if it was the same density, it would be 1/64th out of the Earth. But because when you get bigger and bigger and bigger, the pressure is greater and greater and greater, especially in the interior, and therefore the Earth's density is a lot more. So that's why it goes from 1/64th to 1/181st. Pretty major, but still, that's the largest mass relative to the planet of anyone in the solar system. Okay? Now, the mass is big enough to affect the Earth's orbit. I think this shows up on the slide. Let me see. Yes, it does. Now, if the moon had negligible mass compared to that of the Earth, then it wouldn't affect our center of mass at all. We would almost be right there. But as it is, and I don't think this is quite fair, I don't think this is 1/4 of that, but live with it, But since the moon has significant mass, not nearly that of the Earth, the Earth is 81 times more massive than the moon is, but because it is, then the moon messes with the Earth's orbit a little bit. Okay? If it were negligible mass, like if it was 1/10,000th of that of the Earth wouldn't even notice. Earth would be going like this, moon just goes around it forever. But because it is a fairly massive moon, the largest in the universe relative to its planet, it pulls our center of mass over, not outside the center, it's not on the center anymore, not outside the Earth's radius, but still somewhere out there. So when the moon goes around, this one stays still, so the Earth wobbles a little bit like that while the moon's doing like this, but the Earth does move like this. So you see you have this kind of motion going on. Wherever the moon is pushing or pulling on the Earth a little bit around the center of mass. So you see our orbit around the sun is not a straight line or smooth curve like this. We wobble a little bit because of the path of the moon. Our center of mass sort of follows the moon a little bit. Okay? Our common center of mass, which, again, reflects the possibility that it actually came from us anyway. Now, let's talk about the moon's phases. When you see that crescent moon there, what is making the crescent there? Is that the Earth's shadow? No, not at all. Not at all. That is just that my sun anymore. Okay. If we were here, okay, let's get a sort of at night here. We can't see the sun there, but the moon's over here. Now, if the moon's up here, the full face of the moon, now it wants to be the sun again, I can tell, okay. The full face of the moon is, that we can see above us here is being lit by the sun, completely, okay? Now, when the moon's over here relative to us, only that little bit there is being lit by the sun. That's what causes that crescent moon, the sliver of a moon. So, the phases of the moon result from the changing relative positions of Earth, Sun, and Moon. The new moon is when the moon is on that side of the Earth. We're over here, okay? And the moon is over here. Even if we could see it, none of it would be lit because the lighted side is facing the sun. Okay, the moon's not giving off any light itself, it's all reflecting off the sun. So the only time we see a new moon is just almost at sunrise or at sunset. The moon will sort of be there, okay, but only at sunrise and sunset. And that's why sometimes when you look out there in the early morning hours or the late evening, just before sunset or right after sunrise, you'll actually see the moon, but it won't be bright. You just sort of see the dark side of the moon. Same side we see otherwise, but now it's completely in the dark. So that's the new moon. The first quarter moon would be, we're here at midnight, and it would be right about that, the moon would be right there. So we'd see that side lit, this side dark. Okay? Full moon, back here we see it all lit. Okay? Last quarter, over here, we see the front side lit, the back side not. So those are the phases of the moon. The same side of the moon always points toward the Earth, which doesn't mean the same side of the moon always points toward the sun. So it rotates once each revolution. So its day is its year of us, you know.
So what we call the dark side of the moon, it's not the dark side. You ever heard of the dark side of the moon?
Yeah, there was I think, was there a movie? I know there's a book written by that title. But what that is the side of the moon not being lit. Yeah. The far side of the moon we never see, whether it's lit or not, because it's never facing us. Only people that have seen it, the astronauts that have gone around it, okay? But the dark side of the moon is the side that's away from the sun.
Does the moon have an ecliptic that it follows? Or?
Yeah, it does, of the Earth. You know, it follows that. And it's off of our, the axis around us. So just very occasionally, and that's why when I did it here now, remember, if we were really going to be to scale, I'd be on down the hall for a ways, and the moon would, you know, because you're a long way away, the sun's a long way away. But because of that, it's not down here, otherwise we wouldn't see it when it's a full moon because it'd be in the Earth's shadow. But it's usually here or something like that. And so yeah, it does have an ecliptic that is not the equatorial around us. Okay. The same side of the moon always points toward the Earth. Now, this is what I was just trying to show. Now, there's several things really sort of bizarre about this. The scale is nowhere close to right. Okay. This shows the moon just being a little bit smaller than the Earth. It's not, okay? It's 1/4 of the radius of the Earth. If that's the diameter, that would be a radius. That would be the moon's diameter, okay? That would be all the way across. So this is not to scale. This is not the sun here. This is just the direction of the sunlight. Now you're going to see something very similar to this on the lab with a couple little changes. For some reason on the lab they have the sunlight over here, okay? So you'll draw your moons exactly opposite of this one. You'll have the light side always toward the sun, the dark side always away from the sun, okay? Same thing with the Earth, okay? The other thing that's different on the lab, you'll have some other positions of the moon in between here. You'll have twice as many. These are just your quarters, okay? Sunlight, the sun's over here, the moon back here, you see the full moon. Up here and down there, you see a half moon. This is called the first quarter. This is, okay. They start with the new moon, so let me start with the new moon. It's starting with the new moon. When the new moon is between us and the sun, then we will have you don't see anything except the shape of the moon because the side toward us is not being illuminated. There's the dark side of the moon toward us. We just can't see it because it's dark, okay? That's the new moon. This would be the first quarter when it's rotated halfway. Notice it's going around counterclockwise also. And then full moon over here, all of that side's being lit. Over here, half of it's being lit again, but this is called the last quarter, or fourth quarter. No. That's a football game. What do they call it? I guess first and last. Okay. And then there's the new again. Okay. But this side is the only side that faces the Earth. Down here, that's the side that faces the Earth. Half of it's lit and half of it's not. Here, the only lit side. But it's still the same half as this one. It always stays facing the Earth. Only part of it will be lit, but that same side is all that we see facing us. Okay. Here is something, this figure's in your book, figure 16, and by the way, the last one was too. That was figure 1629. Here is 1630. Okay? All right. When you see a crescent moon, you know where the sun is. It's on the bright side. It's always, picture that as a bow, and from the tip to tip, string your thing, pull it back. That's pointing, the arrow is pointing straight toward the sun. Okay, the sun can't be anywhere else but the side that's lit. So in the either early morning or early evening hours, the part that's lit on the crescent moon is where the sun is, not away. Okay. Now, as the moon turns relative to us and we get a bigger and bigger crescent, you finally get to a half moon, and we'll talk about that in the lab, some of the terminology there. Now, before we move to this, myths, mistakes, and misunderstanding. Here they name 3 moon mistakes. It is a common misunderstanding that the Earth's shadow creates the monthly moon phases. We negated that at the very beginning. That's just a portion of the moon being lit. The other part is not being lit. Okay? Nothing to do with Earth. Number 2, a phrase that you may have heard. I can remember my mom saying this a lot. Oh, that only happened once in a blue moon. You ever heard that? What in the world is a blue moon? Now, if you would have asked me that before I started teaching this course from this text, I would have said it's when you have 2 new moons in a single month, because the moon isn't lit, it's blue. Not true. It's not a reference to the color of the moon. Instead, it's a reference to the extra full moon that occurs in a season, which normally has 3 full moons. This doesn't happen very often, therefore once in a blue moon would be. So it's the extra full moon that you have, like in 1 month. You've seen on calendars, you'll see each of the phases of the moon. The new moon, the first quarter, full moon, and the last quarter. And usually you'll see one of those every month. every now and then, whatever the first one was, you'll see it as the last one, because our months are longer than the synodic month, okay? Synodic month is 29 and a half days. 11 of our months of the year are 30 or 31 days, okay? So we're a little bit longer than that, but it's not very often you'll see two phases on the same. But once every 4 of those, you'll have 2 full moons in a given month. That then will be your blue moon, okay? It's not very often. Now, number 3 says a popular myth has more accidents happening during a full moon phase. However, studies have found no statistically significant relationship between the accident rate and moon phase. This myth is probably the result of people remembering the full moon, but not remembering the other phases at an accident. Okay? I want to take a little exception to that. I think this has been documented too. At least I've heard people tell it anecdotally. We one time had a really weird, nasty, obnoxious neighbor, okay? He lived across the street and over one house from us. And it wasn't just to us, it was everyone in the neighborhood. He was totally obnoxious. And it did seem like on full moons, he did something stupid. I mean, not every full moon, but just about every time it happened, we would notice, hey, it's almost a full moon. And I've heard people talk about in psychiatric hospitals and other things like this, it seems to follow that. And in the lab, the first part of the lab will talk about some of that. What is, I think it's either Greek or Latin name for moon? Does anyone know?
Moon?
Yeah.
Like Mooney?
Lunar, yeah. Lunar eclipse, that means a moon's eclipse. Okay? Let's put one more syllable on that. What do you have?
Oh,
Lunatic. Okay, exactly. Obviously, it's happened enough that people associated weird behavior with the faces. Now, I'm not saying accidents. Maybe accidents don't happen more frequently there, but I think there is something that goes on in people's heads on full moons. I don't know what. So anyway, let's look at the eclipses of the sun and moon. Now, like we said, and you asked an excellent question, does the moon follow an ecliptic? And it does, okay? Most of the time, it's angled between the sun and the earth and the sun and the moon, or the moon to the earth to that, is a fairly good angle. It seems like it's at least 5 degrees or something like that. Yeah. The moon's orbit is inclined 5 degrees from that of the earth. So if we're going along here, 5 degrees, has something like this. So most of the time, the earth is not in the way of the moon, and the moon's not in the way of the earth. Okay?
5 degrees of the celestial equator.
Yeah. Of our equator, 5 degrees, which is fairly significant. Not huge, but fairly significant. Now, for an eclipse to happen, the earth, the moon, and the sun have to be in proper alignment. And this is where all the figures we're going to see sort of distort things pretty badly. Because, like I said, if we were to get the distances right, I would be halfway down the hall, and the moon would still be maybe an arm's length away from the earth, because there's a huge difference here. Huge. Okay. So what has to happen for an eclipse is either those rare times when the earth is between the sun and the moon, or when the moon's in between the sun and the earth. Most of the time it's here or somewhere else. Here or somewhere else. But every now and then it will be directly. Now, a lunar eclipse has to happen on a full moon, right? Because the moon has to be on the opposite side of the earth. So when it's a new moon, a first quarter, third quarter, or anywhere in between, you can't possibly have a lunar eclipse. Similarly, you can't have a solar eclipse unless it's a new moon, because it has to be on that side, okay? So, and new moons only happen once a month, and for the alignment to be perfect, it doesn't happen very frequently, okay? Proper alignment of Earth, Moon, and Sun. They may be on the same plane, but off at the side or something like that. That won't cause it. Now, here's the other thing. And I think I'll use the figure here. Okay. There's one thing I wish they had done in this figure they didn't do. And they didn't do it in the book either. Obviously here, the sun is somewhere way over there. Okay, right? Because here's the shadow of the moon. The sun has to be somewhere over there because the shadow of the moon is going back like this, right? Well, I wish they had shown the Earth is also going to have a shadow that goes like this, right? Same type deal, and it's a shadow like this, and it's a conical shadow, not comical, but conical, cone. Okay. Now, remember, the incline between the Earth's orbit and the moon's orbit, that's a 5-degree incline, okay? And it can only happen when, okay. See, this right here would be pretty close to a new moon, maybe early crescent or something like that would be what you'd be seeing from the Earth there. But you see the shadow is nowhere close to the Earth. Nowhere close. Even if this were rotated around here, it would still be missing the Earth, okay? Because it's in that angle upward, okay? So, if it were to move back here, then it's still going to be, the Earth's shadow would not be affecting the moon at all. So the only place where it would affect is where the moon's ecliptic crosses the Earth's celestial sphere. Celestial equator, you might say. There and there are the only two times. And it would have to be that it would be a new moon here, full moon there. If the sun's out there, and any other time, if the full moon happened here, happened when this was twisted around and they weren't crossing, not going to happen. You're not going to see it. Okay. So, you have to have that proper alignment. The right dead on, not 5 degrees different, right on 0 degrees, where they perfectly line up, and the Earth, Moon, and Sun perfectly line up. Okay, now here's a pretty good picture, except for 2 major things. Maybe 3 major things. One, the sun is awfully small here, but it's also awfully close. Because again, if you got the right dimensions here, the sun is 93 million miles away, and the moon, what do we say? No more than 100,000 miles away. Okay, so different orders of magnitude here. So that's why they had to make the sun look smaller, because they couldn't get it otherwise. Okay, but the sun, anywhere in here, none of the sun's light reaches, and you call that the umbra. That means dark. Okay, umbra means dark. I used to be, I guess I still am, a soil scientist. A very dark soil is called an umbric because it's very, very dark. But in these areas, some of the sunlight gets through, some of it gets blocked. That's called a gray area. Okay, that's called the penumbra. Here it's totally dark because none of the sun's rays make it past the Earth. Now, let me show you this way. Yeah, this is hard to do. I used to have it here, okay? Okay? If I could stay still. This is the umbra, and you see the little fuzziness around there? That's the penumbra. I can't get, as I get closer, you can see a little bit bigger penumbra. That's the umbra. Now, when I get like this, it's all umbra. Okay, you can't see any penumbra. Okay, but that's what we're talking about, the gray part as opposed to the black part. And because of the relative sizes, sun, moon, and earth, and by the way, the earth is not nearly this big compared to the sun. Maybe compared to the moon, it's not bad, but yeah, this is just an illustration. But when the moon does come in between the earth and the sun, not in part of that 5 degrees that would not be blocking it, but right in the middle, right in that place where the ecliptic and equator crosses, then it's going to form a very small, narrow band, which is, there's the total eclipse of the sun. Total eclipse of the sun. Out here, you'll see a partial eclipse of the sun. Remember Carly Simon singing about that guy who was so vain? He went to Nova Scotia to see a total eclipse of the sun. Okay. Y'all wouldn't remember that anyway, would you? It may not have been Carly Simon. It seemed like it was. Okay. So very rarely will there be a total eclipse of the sun. Now, what I want you to do is mentally flip this around. Can you do that? So you have the earth here, and it forms a much bigger thing and shadow. The earth, the moon comes in here. There's a bunch of umbra here that the moon can cross through. So you will see lunar eclipses far more frequently and over a much wider area. And then you'll see partial lunar eclipses if you're in the penumbra. Okay? But because you see the Earth's shadow is a much bigger cone and the moon's smaller, boy, it can be anywhere in there and still get a little bit of time when it's going to be a total lunar eclipse. Okay? Now, solar eclipses are where the tip of the umbra touches the Earth. Now, remember, the moon's orbit around the Earth is not circular. There are times when it's further away and times when it's closer. If this happens to hit at one of the times when it's further away from the Earth, the umbra doesn't quite reach. So then you'll see a ring around the moon, and that's called an annular eclipse. When the umbra doesn't quite reach the Earth, and you'll see just the moon with a ring around it. Okay? That's an annular eclipse. Okay? It's only when the moon is close enough that there's that little bit of band around there. Okay. Now the lunar eclipses, that's when it's on the other side, when the moon goes into the Earth's umbra. Earth's umbra is much bigger because the Earth's much bigger, and the moon's smaller, so there's going to be a much wider area and much more frequent that you'll see that happen anywhere on the globe. But it's still not very common. Let's see if this table is on here. No, it's not. Let's look at the table, because there's a very important reason to look at this table. Total eclipses visible from the U.S. in the early part of the 21st century. Guess what happens on August the 21st? I wish we would still be in class. The class would go outside and look at this thing safely. We would look at it, but we're going to be through by then. In fact, I'm thinking it's awfully close to the fall term beginning, somewhere right in that time frame. August 21st is going to be a dark day because we're going to have a total solar eclipse. Now, we won't quite be total. The line goes from Oregon to South Carolina. Remember, it's a pretty narrow little band there. Oregon to South Carolina. Here's Oregon. There's South Carolina. Okay? That line that connects those two is going to be a little bit north of Birmingham. If I'm not mistaken, I think Nashville is. Why can I not see Nashville? Oh, it's on here. Yeah, there it is. I'm guessing Nashville is just about in that. Now that's almost going to be worth the trip to Nashville. I don't know if school's going to be in session. If it's not, I bet a lot of people are going to be heading up to Tennessee so they can actually see the total. We'll see a partial solar eclipse for sure. We're going to be in the penumbra for sure, and we'll see a fairly large amount of it. But up there, total solar eclipse. You will see stars near the middle of the day. Okay? It's going to get that dark. Okay? Now this doesn't happen frequently, like I said.
Did it happen in like 89 or 80? In the late 80s?
There was one, but it wasn't total that I recall in the U.S. Maybe some part of the U.S. was, but not where I was living. I think we had a partial solar eclipse, but it wasn't total. Now, that may have been the year that in Nova Scotia you got to see it. Maybe that's the year Carly Simon was singing about that. He went up there. It was about the time of that song, that whoever he's so vain, went up and to Nova Scotia to see a total eclipse of the sun. But I believe that was about that time period. So you're right. But so far, to August 21st, 2017, this is between 2010 and 2025. Only two in a 15-year period. 2017, 2024. Okay? So let's see, let's count back 15 years from 2010, that would be 95. There were probably two in that time, and then count back, so 87 could have easily had one, okay, or around that time period. I don't know if it would have been total in the U.S. Somewhere in the U.S. it could have been, but not where I live, because I don't. Were you at a place that you think it was total?
No, it got dark.
Huh?
I know it got dark. I remember I was in elementary school.
Elementary school. And where was that? Here in the area here?
Yeah.
Okay.
I was in high school at Lanier.
And where?
At Lanier.
Okay. Do you remember it?
Yeah, I graduated in 84.
84.
Before that.
Before that. Does that sound about right for you? Yours was 87, you think? Or could it have been 84?
What was it?
Huh?
When did I graduate?
Well, that you remember the darkness in the day.
What year?
Could have been earlier.
Yeah, okay. That must have been about the same time. So maybe we did have one then. I'm trying to think where I was in 84. I graduated from college in 73. I was in the Navy till 77. So I was probably in Nebraska. And that may be why I didn't see it, because I would have been. I think we had a partial. Y'all probably had a full down here, so that could have been.
It got dim. We couldn't see stars.
You couldn't see stars,
Yeah,
but it got.
pretty dark.
So you were probably in this part of the penumbra, and I was in that, or something like that. So yeah, it seems like now that you mentioned that, I remember there was, but you see. What we were warned about, so we could see enough of it, you weren't supposed to look. Sorry.
After it got dark, you could look at it.
Huh?
After it got dark, you could look at it.
You could.
And see it. Yeah.
Okay. When it was, if you're too much in the penumbra, on the shallow part of it, you never want to look directly at the sun ever, because that's intense enough radiation you can burn your retina. Because you see your lens in your eye is focusing that light, and that's just too much for you. What you should do, and that's what I was going to say, if we were here having this class on August 24th, we would go over to the welding department and check out one of their masks, and we would look at it. Okay, because it is safe to look at the sun with a welder's mask, because that's not nearly as bright as the flame that they have to do. So that's a safe way to do it. In the newspaper, just in the last couple of weeks, there was a picture of somewhere, and it may have been the time you're talking about, that people, they were using, it's something like sunglasses, like the ones they give you after you've had an eye exam. They're plastic things, but are pretty dark. They were using that to look, and it's safe to do that. But even when it's a annular eclipse that you see just a ring around there, don't look at that very long. You can damage your eye. Now what they do, they can take pictures of it or look at reflections of it. And that's what another thing people would do, would take a mirror and do, and that would be a little bit better. Especially if it was a leaded glass mirror. Okay.
They let us outside, and we, had cardboard boxes.
Yeah, okay.
The hole through it, and you can see, you can actually see it.
Yeah, right.
Like the reflection of it on through the cardboard.
Right, exactly.
And then you can look at the leaves on the tree on the ground. You can see like double leaves and stuff like that. Kind of made the shadows look crazy. Right. You can look at your shadow, and it was kind of crazy. That's why I said I wish we were still in session there. Not that I wish the class would go that long, but but don't miss it. We're going to be in a very small part of the penumbra, close to the umbra. And if you go just a little bit north into Tennessee, I bet you'll be able to see full eclipse. Now, lunar eclipses in that same 15-year period, 1, 2, 3, 4, 5, 6, 7, 8, 9 compared to 2 solar eclipses. Now, these are total lunar eclipses. The last one was September 28, 2015. And the next one will be January 31st, 2018. So next January, we will have a total lunar eclipse, and that'll be right around moonset, which will be early morning. Okay? And that's in January. Pretty cold that time of year in January to be out there right at daybreak. But be worth a look. All right, good deal. Another effect of the Earth-Moon system are the tides. Okay? Any of you fishermen? Okay, I bet you follow the tides, don't you? A little bit? Or you only freshwater fish? Oh, okay, yeah, it wouldn't matter to you much. But if you've ever done any saltwater fishing, those people pay attention to the tides. What are the tides? That's the result of different gravitational pulls on the front and back sides of the Earth. That sounds a little bizarre, doesn't it? 3 factors that enter into the tides. The Earth, Moon, Sun positions. Okay? The spring tides are when these 3 are aligned, and the neap tides are when the Moon and the Sun are at 90-degree angles. So here again, you're going to do the Sun for us, okay? When you're there, the Moon's anywhere in here, same side as you, then that's maximum gravitational pull. Or when the Moon's back here, maximum gravitational pull. Sun is pulling that way, the Moon's pulling this way. So that's when you have the spring tides. It has nothing to do with the season spring. That means the largest tides. Smallest, or the neap tides, are when the Sun's there and the Moon's here, or here, 90 degrees from each other. Then the Sun's pulling that way, the Moon's pulling this way, so you have the smaller tides. Those are the neap tides. Okay? So that's the first factor, is the relative Earth, Moon, Sun positions. And then you can have everything in between, smallest to largest. Yeah. Now, second thing is the elliptical orbit of the Moon. We've already mentioned that. The greatest pull is when the Moon is closest to the Earth, and the less effect when it's farthest away. So it just depends on where the moon is at the perigee. Perigee is the closest point, apogee is the farthest point. Because remember, we're elliptical, perigee closest, apogee farthest. There's a 48,000 kilometer difference, which would be about 29,000 mile difference, okay? So it can make a difference. The size, the shape, and the depth of the water basin, okay? Closest big body of water to us, Gulf of Mexico. Guess what? That's where the effect of the tides are the very least, about 1 foot. Okay, a third of a meter is about 1 foot, is about the average tide difference that you get in the Gulf of Mexico. But if you're in the Bay of Fundy, and I believe that's in Nova Scotia, 15 meter? What did I say this was? About 3 meter thing? I'm talking about a 5-story building from low tide to high tide. How do you tie up a boat with that kind of variation? I think what they usually do is have poles, and the docks and the boats go up and down these really tall poles, okay? And that keeps them floating. That's a huge difference. 5-story building difference, okay? Now, here's what we mean by this. There's a couple of really strange things going on here. Let's just say, and by the way, the moon has the greatest effect, not because its gravitational force is greater, but because it's so much closer, okay? So let's say the moon is over here. What it does is pull on the water of the earth, because you see the water is movable. So it pulls more on the water, and the solid part of the earth doesn't get pulled as much, but it gets pulled a little bit, so you have a bulge back here too. So you have a bulge on this side and that side. So the moon could be over here or over here, and you're going to get almost the same effect. Okay? And if the sun's in that same direction, then that would be a spring tide. Okay? If the sun was over here, then you still get thing, but this would be thinner here and thinner here. Okay? That would be a neap tide. Okay? Does that make sense? And that is the last slide of the section. Now there's a couple of things here. There's a couple of examples. How long does it take a reflected beam of light to travel from Earth to the moon at a distance of 384,500 kilometers and then back again? It's just playing around with the speed of light. And the answer is about a little over 2.5 seconds. So if you were to beam light toward the moon and happen to have perfectly positioned a mirror to beam, get back, you could do a flash 2.5 seconds. A little over that, you'd see the reflection come back to you. The speed of light is pretty fast, so we're pretty fast. How far away is the moon if a reflected beam takes 2.65 seconds rather than 2.56 seconds, okay? It would be about 397, almost 400,000 kilometers away, as opposed to 384. 384 is about average. The 397 would be when it's at its apogee. Okay. Now, people behind the science. Why they chose this chapter, I don't know, but they put Carl Edward Sagan. Y'all ever heard of him, Carl Sagan? He did a series on PBS, I think it was, called Cosmos, was it? He was good. He was really good. He's one of the best science communicators, and he loved space and that kind of stuff and the stars. What's that again?
He loved that billions and billions.
Yeah, right. Yeah. I never watched them very much, but I swear I think my older brother has read every book he ever wrote. He loves Carl Sagan. Now, this can't be your source. If you choose to write on Sagan, this can't be your source, but it can lead you to your source. Okay? Now, in reality, he was an okay scientist, but he was a much better communicator of science. Okay? He didn't do anything outstanding necessarily, except he knew how to talk about it. And he did a great job doing that. Okay. All right. There is a summary here, which is one of the longer summaries I can recall seeing. So, again, I'll say this. Don't neglect reading the chapter. Okay? But once you've read it, I would say a time or two, or three, or so, then review the summary. This hits the high points. It doesn't hit everything, but it hits the high points. And again, a very long list of key terms, longer than most chapters. They list them alphabetically, but they do give page numbers where they were first referenced, identified, or described are there. Applying the concepts now, 47. That's about average number of questions for that. With the answers given, to me, the very best thing to study for the test. Have y'all used this at all in your practice? Okay. If you go through and don't look at your answers, do your best job, then compare that to the answers, then go back and see the ones you missed, why you missed them. If you can't figure out, if you think they may be wrong, bring them to me, and we'll talk about it. Questions for thought? 30. Again, one of the largest numbers of any chapter that we've had so far. For further analysis, 6, that's about normal. Invitation to inquiry, pretty nice one. Don't have to do that, but you might find it interesting. And then if you have the full books, then the parallel exercises, Group A have answers in the back, and Appendix E, Group B do not. So if you're interested in doing some of the exercises, do. All right. We will stop there and pick up on Chapter 17 next time. We're moving out of the astronomy portion into the sort of the geology portion, okay? Earth sciences is a better maybe term for it. So I'm going to, that's what I meant to do. Okay. Wait a minute. I don't think I'm going to end it. Yuck, I probably already passed it. Okay, sorry about that. I'm going to leave it up here in case we need to go back and reference something. Okay? Now, here is the lab for Chapter 3. Okay? Again, we may not have time to finish it, but oh, we didn't do that?
Yeah.
Oh, 16. Oh, that's going to be next time. Okay, I was thinking 15. We should have told them. Huh?
Thursday?
Yeah, Thursday. The last 30 minutes on Thursday. So we finish the chapter today. So the exam will be the last 30 minutes on Thursday. Now, if you don't feel ready for it then, you can take it Tuesday. I mean, anytime during office hours. Remember, I have office hours on Tuesday and Thursday, 2 hours before class and close to 2 hours after class.
It's an interesting website with many clips.
Oh, nice. Is that what we're going to see here in Birmingham?
Starting exactly at 12 o'clock, lasting almost exactly 3 hours.
Wow. Okay, show me the maximum amount. No, go back to what you just did.
They get it on the chart here.
Oh, look at that. We're almost completely in the umber. Just a little bit out. In fact, I wonder if we went just as far as Huntsville, we might be able to see that. Now, what day of the week is that? Did it say?
It didn't say that. So
Okay.
it's 21st.
20. Yeah, that's all right. You don't need to do it. So anyway, that yeah, you're going to see stars that day if you're here in Birmingham. That little bit of sun that you'll see, that's not going to keep it from seeing the stars. Now, also, and by the way, your lab's right there on that desk. Okay. Also,
It's going to be on Monday.
it is a Monday, shucks. I was hoping it was a weekend. Okay. But I bet you that's the first day of class. I mean, the first day we come back, I bet you we're going to be in stupid meetings. I'm going to say we got to take a break, and it's right at noon. You said is the maximum.
It starts exactly at noon.
It starts exactly at noon, and the maximum is about 1:30. Okay. If I'm in a meeting, I'm going to say, let's postpone the meeting and go out and see the eclipse. Okay. You can't do otherwise. Okay. All right. We are still recording. Okay. Let's get started on the lab. And this time I only made 4 copies because I thought these other folks aren't coming. So, first thing you're going to do is read the lab, okay? The first page, now, there's not a lot of really heavy stuff on that. They talk about moonstruck and lunatic and that kind of stuff, things we've mentioned before. And by the way, I had forgotten this, that the Muslims base the Ramadan, I think. I thought it was that. But they continue to live by cycles of the moon. So I bet you their Ramadan, that's why it changes year to year, because it's exactly so many cycles of the moon, and the moon's not exactly on the same cycle as the Earth and Sun. So that's why that changes. But I'll let you read as much or as little of that as you like. But what it says at the bottom, using about 6 observations of the moon over a 2-week period, you will examine how the moon changes position in the sky and how its appearance changes as it moves. Okay? So here are the observations you will make. Now, I can't say you'll start tonight, okay? Because I want you to do, okay, I'm getting ahead of myself. Complete cycle of the lunar phase is about 29.5 days. We said that before. You will follow the moon for at least half of a cycle. Because guess what? At any given time of the day, you can see the moon for half of that cycle, and the other time you can't, because it's going to be on the other side of the Earth at that time. Okay? So you've only got about a 2-week period to see it at any given time. During this time, you'll be recording 3 things. Okay? The first of these, or one of these, is how much of the lunar disk is illuminated. And this is a judgment call on your part. Is it half, between half and 3/4, between 3/4 and full, between 1/4, less than a quarter? You make a judgment call on that. And you can draw little pictures if you want to. But before this happens, and this could start as early as tonight, okay, let me back off again. You get 2 choices here. First choice is when you want to do this. For me, evening would be great. I put the dog out just about every night at 10 o'clock, or sometimes shortly after 10. I try to do that the same every night, okay? We want her to stay up as long as possible so the chance of accidents is minimized, okay? So I usually try to put her out sometime after 10. So if I were doing this, that would be my time. Somewhere between 10 and 10:15, I would pick a time, try to stick to it, okay? I'm not telling you what to do. You know your schedule. If you're an early morning person, you get up before the sun comes up, you might want to do it early morning. If you're a late night owl, 10 o'clock may be way too early for you. If you're still partying at 10, that wouldn't be a good time. Y'all be doing that, okay? Okay, so you pick the time, okay? You pick the place. So that's what number A is. So actually B is the time, but let's do A then. You will need to find a spot with a relatively unobstructed view of the horizon and sky. Good luck with that in town, okay? It's just not going to happen very easily. Okay, let me give you a few hints. I had a student sat right over there. I can't remember which desk, one of those two desks there. Good student, and he was also a work study student here, and he always worked in the evening. He was the desk, the front desk on the back side of the building. He manned that, helping the evening coordinator. That was his work study job. And he got off, I don't know, 9:30, 10, whatever time he got off was the same every night. So he went out there to the parking lot, and that's where he did his observation. Pretty clever, okay? Now, where I live, there's no unobstructed view, but I can get up in the backyard and have as unobstructed view as possible, okay? It's not good, but it's the best I can do in our backyard. Our front yard is pathetic. Trees, it's in a hole, you don't have much. Backyard would be better. That's what I would choose. If you happen to live near, say, a Walmart parking lot or something, a shopping center parking lot that's safe to go to, whatever time you choose to go to, that may be a really good choice, okay? Because at night it's probably going to be pretty vacant, okay? If there's a security around, be sure to let them know you're going to be out there making observations. You'll probably be okay with that. If you happen to live near a sports field, baseball field, football field, soccer field, something like that, that may be a pretty good choice. If it's okay for you to get there at the time of night you're going to, and it's safe. I don't want you to do anything that's not safe. You choose the best location you can, okay? Now, when I say choose the best location, it's just not anywhere in the parking lot. I can't think of the guy's name. When he went out in the back part of the building, he probably went to one parking place and used that same one every night. Okay? If you're in a Walmart parking place, I don't know what to do. Maybe take a little can of spray paint, make an X on it so you can always go to that spot. They probably won't mind that too much. No one will notice it, do something like that. If you're using a baseball field, maybe a little harder. Get you some chalk dust or something like that. I don't know. Find something that you can sort of figure out you're going to the same place every night. Okay? So you'll need to find a spot with a relatively unobstructed view, the middle of a large open space with a few low-profile landmarks near the horizon is ideal. You will need a little ambient light to make some sketches to record your observations, but you should not be near any bright sources of light. Therefore, a Walmart parking lot, especially if it's an all-night Walmart, they might keep the lights on, and it might not be a great place to be. A ball field might be pretty good if the lights are off. If the lights are on, terrible place to be, okay? But it's important that you use precisely the same location for all of your observations over this 2-week period, okay? So try to find a place that you can be sure you're at that same spot. If there's a power pole in the middle of that parking lot and you want to be a certain distance from that or something like that, or right at the power pole, that would be okay. In a baseball field or soccer field, I don't know. You just have to find something that will work for you. Maybe right behind second base if it's a baseball field. If it's a soccer or football field with lines on it, 30-yard line right in between the hash marks or something. Find some place you can go to. Okay. Timing your observations. Now it says, I will give you general instructions. The choice of the time of day that you're going to do determines on what days you will be able to do it. Morning, the moon's not going to be the same place as it will in the evening, so I can't tell you that. So you choose, and what I would say is go out. Now tonight it may be raining. In fact,
It's supposed to rain the next week and a half.
I know, it seems like it's been raining for the last week and a half. So that's why something else that's coming up later is going to be really important. Every semi-clear night that you have, get out there and take it, okay? Advantage of it. Because right now, I can hardly remember a rainier period than we've had now. I'm not complaining, but man, it seems like just about every day, okay? So, try to get out of there in between showers or something like that. So if it's tonight, if it's the time you've chosen,
at the place you've chosen, and it happens not to be raining, go out there tonight. If it is raining, wait till tomorrow night. And you go to the first night you can possibly get there that's not raining. And here's what we'll get to that in a minute. Choose a time of night convenient to you for observing the moon. Once you choose the time of night for observing, it is critical that you make all your observations at the same time within 15 minutes of each other. That's why I said if I put the dog out at 10, I would probably choose to do from 10:05 to 10:10, because hopefully, I also put the trash out and the recycle out and stuff like that. So I would choose maybe 10:15. That would be a good safe time. I know I wouldn't be there any earlier than 10, and hopefully no later than 10:30. Except I teach here until 9:15 on Mondays and Wednesdays, so I might have to make it a little later for that. Okay, you choose. Because the weather may hamper your observations over the course of the observing period, you do not want to let many clear nights go by. Like you said, we may have a week and a half of cloudy nights. If it's not raining, it can still be cloudy. That could be a problem. But I'm not even sure the moon's up right now. I remember seeing it about a week or so ago, so it may not even be up. So maybe we're going to look out, and by the time we get through the rainy thing, it'll be about the time it's going to be out there. After your first observation, After your first observation, which might require half an hour, so I would be there at least 15 minutes early and be a little, do succeeding observations of the moon will require less time, maybe about 5 minutes. Okay, I don't think they'll need to be that long, but it might be. So here's what you report. Now you can do it any way you want to. If you want to take a notebook out every night, maybe with a little pen light that you can write by or something like that. My wife has these clips that goes on a book, I would probably steal one of hers and take that there and do it, if you need it. But if the moon's out, you might not need it. You might be able to write it there, okay? In order to record the appearance of the position of the moon, you'll need to make sort of a scale drawing of the moon in relation to the landmarks around your observing site, okay? Now, let me just this is far easier to do in the winter than it is in the summer. If I were choosing this spot, which I wouldn't, to be my spot, I would look out there and I see a power pole that has a lot of guy wires going up to it, or some sort of thing, lots of guy wires. That would be one of my things. I see over here, I'm going to have to move because I don't have a big field of vision. See something blue there. I don't know what the heck it is with a box on top. That may be one. I look around and find various things. A tall tree. I've got my spot. I'm going to be in my spot. And I'll look around and pick out the things that are on the horizon. A tall tree, a power pole, things that I'll see as I go around the horizon. Okay? And therefore, when I go out to observe the moon, I'll find the one of those that it's closest to. It may be off some. And say, okay, the power pole over here. If I go up, and here's what I would do. You can do it any way you want to. They describe here. In fact, I'll read what their description is, and I'll tell you. The first night out, even if the moon's not out there, go find your landmarks. Okay? And go around and estimate. If you know where true north is, start at true north, and then start going around to the east and go around like that. If you don't know true north, pick a landmark and say, starting there, I'm going to go, about this far from here, that far, and stuff. You go from that one landmark you want to start with. Whatever you want to start with, go with it. Okay, make a sketch if you want to. They say a poster board. I don't require that. But do drawing paper, anything. Just make a sketch of what you see around you. Landmarks, trees, buildings, power poles, street signs, whatever. I mean, what do you call those along the road? Billboards, okay? Whatever, you happen to see. Okay.
And like I said, you may want to go out initially about half an hour before your optimum observing time that you have chosen so you can get a complete listing of your landmarks. Or if the moon's not out, do it tonight. Take as much time as you need. So those landmarks aren't going to change. So your fixed spot, they're always going to be there, right? Don't pick a car that's moving. That's not going to be a landmark. Yeah. So pick things that are fixed. Now, it says make a scale drawing. Again, that's up to you. If you don't want to do that, if you can remember by, your notations, that'll be fine. Okay. Now here's how they say to do it. I don't find this optimal, but here's what they say. The width of your outstretched hand, they say, is about 22 degrees. Okay? I'll buy that. The width of your fist is about 8 degrees. The width of your 3 middle fingers, don't just do one, no, never mind, okay. That's about 5 degrees. And the width of your index finger, make sure it's the index, okay? You don't want to get it, okay, never mind. That's about 2 degrees. Okay? Would I do that? I don't think so. Okay? A convenient scale to use would be 5 degrees in the sky and a landmark corresponding to 2 centimeters on the drawing. You can do that if you want to. If you read this, page 381, the third paragraph down, alternately, you could carry a ruler with you and measure the dimensions and separations of the landmarks with the ruler held at arm's length. That's what I would do. Take a ruler out there. Probably a 1-foot ruler at arm's length is going to be sufficient. If you want to take a yardstick, do that, okay? And then, like I said, if you find the moon the first time you find it, and you go around, it happens to be that power pole is the landmark it's closest to, then hold the yardstick out at, or the ruler out at arm's length from the top of the pole, the horizon, whatever you choose to do. It's 9 inches up and 2.5 inches over to the left. There it is. I don't do hands and fingers and things like this. That to me would be smart. I mean, that's what I would use, the ruler. But you can do it if you want to do the other thing. To plot the position of the moon on your drawing, you will need to make 2 measurements. Okay? And I just said how far up from your landmark and how far right or left from your landmark. If another night is over here and you've already determined these landmarks, move to that landmark, that billboard. Okay? 6 inches above the billboard, 4 inches to the right of the billboard. Okay? You make the things, but you've already determined the first night you went out there, you've identified your landmarks, evenly spaced, fairly evenly spaced around your spot that you're not going to change from, and you've identified those, and then night to night you go through that when you're observing the moon. So that's the first. The position, the relative position of the moon from the Earth's landmarks. That's the first thing. Okay. Number 2, and they don't list them this way, but go about 2/3 of the way down the page. And by the way, would be ideal. The first night you see the moon, that's your night 0, okay? And then every other night from then on, if it's a clear night. If it's not a clear night, then go to the next night. Don't wait every other. Go to the next clear night you get, and then start over every other night. Okay. It's good to get 2 nights in between because you have more movement. But if you don't, get every clear night if you can. Okay. Now, you've gotten the location of the moon relative to the Earth's landmark. While you're doing that, note the relative appearance of the moon. The moon looks like about half, between half and 3/4, between 3/4 and full. Just a tiny sliver, about 1/4, between 1/4 and 1/2. Whatever. You give a description of that. Okay? Now, they give you a couple of hints. You might take a coin, like a quarter, trace that on a piece of paper, and then estimate the amount of the moon that is lighted. So what I would do would be the part that's not light, and darken that part and leave the other part light. Okay, whatever. Okay. Now, about 4 paragraphs up from the bottom of page 381. Record the position of a few bright stars near the moon on your first observing session. Okay? So that first night that you see the moon, that's the one they call day 0 or night 0. Then, when you see the moon, try to find a pattern of bright stars near it. Okay? If it's anywhere close to the Big Dipper, use a Big Dipper. If it's close to Orion, use Orion. If it's not close to either one of those, pick this pattern and draw that pattern on your piece of paper. It's fairly close to this. And take your ruler, so many inches above or below this, so many inches right or left of that. Okay? So observe that. Okay. Now, it's really great to be able to talk in terms of north, south, east, and west too. So if you have a little compass, you can take that. I have a few downstairs. If you want to take those and use, please bring them back. Okay? But if you have something, or if you know what north is, then you can just go with that. Okay.
You got a compass on your phone.
Yeah, and if you got a phone, you got that. Okay, yeah. If you know how to use your phone. Okay, right. I don't. Okay. Now here are the questions you are going to answer when you turn in this lab. You've taken all these observations. Here are the 3 questions you're going to answer. Bottom of page 381. How would you describe the night-to-night path of the moon with respect to the landmarks around your observing site? Okay? You might say, this would be one way to say it. When I was facing due north, the moon started on my left hand and climbed and did blah, blah, blah. Or it started here and did blah, blah, blah. So describe it relative to your landmarks. Okay? That would be going north, south, east, west, or right, left from this landmark, or something like that. But describe the night-to-night path of the moon with respect to the landmarks. Number 2 question, the one at the very bottom of the page, in which direction does the moon move with respect to the background stars from night to night? That's why it's important to pick out some pattern of stars relatively close to the moon and look at that pattern night after night after night. It could be the moon moves way away from that pattern of stars. Note that. Okay? Note that. Okay? And the third thing, go to the next page. It doesn't have a number on it, but right here is a graph. Day 0, you put on the vertical scale what portion of the moon you see. Is it a quarter moon, which would be a small sliver, half moon, exactly half of it, 3/4, okay, or a full moon? Or if you just see the shadow of the moon, that could be a new moon, okay? But you pick that. And then 2 days later, if that's when your next observation is it bigger or smaller? Go up if it's bigger, down if it's smaller, okay? That's why it's good to have 2 days. You'll notice a difference there. Another 2 days, which way is it going? You know, so you make a plot here. They give you 20 days here. You're not going to see the moon for 20 days. You'll see it for about 14. Okay, and every other day you could get 7 observations in. With rain, maybe only 6, possibly only 5. Try to get as many as you can while you can, weather permitting. So that's the third thing. You're going to make a graph of the moon, of the size of the moon as you've been looking at those days. And you might want to put under day 0, June 21st, you know, or whatever day that would be, and then count your days from there. That's your observations over the next, it could be 2, 3, it could even be 4 weeks. Like if the moon just went down yesterday, and you're not going to see it for another 2 weeks, you might not be able to see it for 2 weeks, and then you do 2 weeks after that. I think we've got time enough in the term for you to do that. If it's up there now, it may only be up there for a few days, so you may have a few observations out, have to wait another 2 weeks, and then you get a few more observations. It'd be better to get it early in the cycle if you can. But
Summer term, you just don't have a lot of flexibility with that. Okay, that's the part you're going to observe. Okay, that took most of the explanation. Now let's get to the part we're going to do in class. How are we doing on time? We've got 20 minutes about. I think we can get most of this done in 20 minutes. So what we want to do is Part B, lunar phase nomenclature. You got to read that, okay? I'll let you do that whenever you want to. But our observations are going to be on page 383. So turn to that page. And like I said, okay, there it was. You're going to do something that's very close to this, only different, okay? Notice on your slide, the sunlight's coming from the right side, not from the left side. And also, they've already drawn the earth in for you, and see, whereas there, the white half is toward the sun, dark half's away, you're going to have the white half toward the sun, dark half away. So yours is, they've drawn that for you, okay? They have 8 other moons here. They only show 4 here. So what you do, this is where we began, not up here at the top, but here. What you do is draw a vertical line through each of those moons. You got 8 moons, draw a vertical line through each of those moons. Right? And then the left-hand side of that, color that in. Now, if you've got pen, I would say use a pencil. But if you're sure you're not going to make any errors, you can use a pen. But if you make errors, you got to redraw it. And I don't have any extra copies. So if you got a pencil, I'd say go with a pencil. I've got 1 up here, 2 up here. This probably has a better lead point than mine does. Anyone else need a pencil? Are you okay? Okay? So the first part of this, and that thing in the middle of the page, draw a vertical line between down all 8 of those moons, and the left-hand side of that darken in, the right-hand side leave white. Everybody see and understand? Okay. If you have any questions, ask. Don't mess something up. Okay? Very good. Y'all are such a good class. All right. Here, do this one good look. Looks good. I can't see from here. It looks good. Fantastic. All right. When you get all 8 filled in, look up and let me know. Got it? Good deal. Huh? Say that again. Darken the left-hand side. Just like here, the right-hand sides are darkened. You'll do it because the sunlight coming here, you'll darken the left-hand side. Just like the earth is darkened here. Okay? All 8 look identical, just like these 4 are identical. Half is dark, half is light, always the same. Okay? Ready? Did you finish all 8? No, okay. Yeah, you got those 8. Okay. Now we go to the bottom of the page. All right? Now, remember, everything's turned around backwards here because we got the sun from the other side. So to have this equivalent, this would be your number 1. Your number 1's on this side, but because the sun's on this side. So that would be equivalent to the number 1 here. So I'm going to call this number 1. Okay? If I'm here and look at the moon here, what do I see?
I'm on the earth looking at the moon. What do I see? Only the dark side. So number one below, darkening the entire moon. Everything's dark, right? You buy that? Okay? You get that done, then look up at it. You already finished yours. Okay. All right, move to number 2. Now number 2 is on here, but it would be right up here, looking exactly like this, number 2. Okay? Okay, actually, I'll make it down here because we're going counterclockwise, so I'll make it down here. You're on the earth and look down here to see that moon. What do you see? This isn't on this one. What do you see? You're looking down at this, and that's that moon. You've already drawn it in. Yours is up here. What do you see? You see just a little sliver of light toward the sun, right? So do that. Make sure it's less than half, just a little sliver of the sun, but of his light. So most of it's dark, not all of it. All of it's dark like this, but most of it's dark except the little sliver that is closest to the sun. So on the right-hand edge, there's just a little bit. So what I would do is draw a little sliver. I'm probably doing too much, but because I want y'all to get it right. Okay? Here's your, that's an ugly moon, isn't it? Here is your moon, right? That's what you had. You're looking at it. So, what I see from here, as I'm looking up here, and see this moon, dark here, right? I'll look up and I see just a little, okay, again I'm going to draw the thing. I just see it, that mark is light, this mark much is dark. I'm not going to do it all, but you see that's what. Always have the lighted side to the right because that's where the sun is. Y'all see what I'm talking about? Did you have it? Okay. I'm not going to do too many of the rest of them for you. You tell me what you see. Now, not this one, but yours here. You look up at that, what do you see? Exactly half. Only your white half is here, your dark half's there. So draw another vertical line. In fact, it looks just like the one you have for number 3. And your number 3 below looks just like that. So number 1 is completely dark. Number 2 only has a little sliver toward the right that's light. The rest of it's dark. Number 3, half white, half dark. Color in the dark half. Okay. Okay. Everybody got it? Number 4 is over here. What do you see?
Like 3/4.
Okay, very good. That time I would do my little sliver this way, but only darken in that little sliver and leave the other right hand half, 3/4 of it white. That's number 4. Everybody got it? See why? Okay. What do you see when you look at number 5?
Full.
Okay, so how do you draw that? Don't touch a thing. It's already full. Number 5 is completely lighted. Okay, you got it. Number 6.
Number 6 will be back to
Just like 4. Exactly. Just like 4. You see most of it lighted, the part toward the sun, only that back sliver is dark. Just like 4 at the bottom, not like 4 at the top, 4 at the bottom. Okay? Everybody seeing what we're doing? Okay? How about 7?
Just like 3.
Just like 3, you're absolutely right. The right half is light, the left half is darkened. In fact, just like 7 above, just like 3 above, just like 3 below, they all look identical, right? Okay, good deal. How about number 8? I like 1. 2, just like 2. You have that little sliver, there it is right up there, little sliver to the right, leave that lighted, darken in everything else. All right. Everybody got those? Okay, now we're going to go back to the previous page, 382. A totally dark moon is called a new moon. That's in the second paragraph there under Part B, winter phase nomenclature. Okay? A few days earlier or later, you see just a sliver of the moon, like that one right up there, of the lighted side of the moon. That's called a crescent. C-R-E-S-C-E-N-T. Okay? Your first and last quarters that they show here, and you have, those are called half moons. You could call them first quarter moon and last quarter moon, or you could call them half moons, whichever you prefer. When more than half is lighter, like you saw in 4 and 6, in 4 and 6, we call that is sort of the opposite of this. This part's light, a portion of it's light on this side, and just a sliver is dark. You call that a gibbous moon. G-I-B-B-O-U-S. Okay? And on either side of the full moon, those are going to be gibbous moons, because most of it's light. Down here, it's going to be a half moon again, or you can call it a last quarter, whatever you want. Okay. Now, the second thing to note down here, the last paragraph here, when the moon is increasing the amount that is being lit, that is called waxing. When it's decreasing the amount that's being lit, that's called waning. Okay? So go back to the top of 383 and refer to the bottom of 383. Why they put it together in this manner, I don't know. Okay? Well, I sort of do. These two on the bottom half of the page are figures, and the thing at the top of the page is text. But if they make that, it's just so weird, the placement of it. So look at number 1 down here and use one of those titles. The title will be new moon, crescent moon, half moon, gibbous moon, or full moon. One of those 5 words there is what you put in number 1. And number 1 happened to be which? Those 5 words. New moon. On a new moon and a full moon, you don't say waxing or waning because they peaked. Okay? It's hard to say which side of they are. So those are the only 2 you're not going to put waxing or waning. But for all the rest of them, 2, 3, 4, 6, 7, and 8, you'll put one of those 5 terms, new, crescent, half, gibbous, or full. One of those 5 terms, and then you will put, now except for full and new, you will put the word either waxing or waning, depending on whether it's increasing in brightness or decreasing in brightness, waxing or waning. All 8 spaces there will have one of those 5 words: new, crescent, half, give us, or full. And 6 of the 8 will have either have the word waxing or waning after that other word. The new and the full don't put waxing or waning after either of those. But the others, the crescents, halves, and give us, be sure you put waxing or waning. Okay? And I didn't say this again, but it's true for every lab. You can work together. You know, I see 2 of you doing that. The other 2 are Lone Rangers, but y'all can compare notes, discuss among yourselves. Sometimes the best learning comes that way. But if you got it, you got it. It doesn't matter. Okay, any questions? Okay. Now, we've just got page 384 to go, and yeah.
So you can tell that you're going into waxing moon after a new moon, right?
Okay, say that one more time.
After a new moon,
Right.
you can start seeing light is going into waxing.
Waxing, yeah. From there until you get where? Full, okay. And between full and new, you're waning. Exactly. That's why you can't say at a new or at a full, whether it's waxing or waning, because you don't know. Might be a little bit on one side or the other, but it's hard to say. So you just leave those off there. Now, we've only got left to do page 384, but technically we don't really have any time left. You want to do 384 the first thing in the class on Thursday. Okay? So first thing in class on Thursday, remind me, we do the last page of this lab. You can think about it. You may even be able to do it at home, but we'll go over it together. Okay? Next, as soon as we finish doing that, we're going to turn around and start chapter 17. Fun chapter, by the way. All of them are fun chapters. Okay? And then the last 30 minutes, I don't think we'll get far enough in 17 to have a lab, but we will, thank you, we will, knock on wood, get far enough along to, all right, good deal. We'll get as far as we can in chapter 17, and then the last 30 minutes, we will have the test. Everybody's hearing this now? We will have the test on chapter 16. Last 30 minutes on Thursday. Second?
Tuesday?
Wait, today's Tuesday, right? Right? Today's Tuesday. I am right? Yeah. Today's Tuesday. So Thursday is when we have the test on chapter 16. Day after tomorrow, Thursday. Okay? Now, if you don't feel ready, you can put it off, but then you'll have to do it during my office hours. But remember, I have office hours 2 hours before this class and about 2 hours after the class. So you can, if you don't feel ready, on Thursday. Okay, we didn't get the last page done, so we'll do that the first thing. So first thing on Thursday, we'll do the last page of this lab. And if you have any questions, we'll answer questions on it. And questions on the chapter. Then we'll get started on chapter 17 and do as much as we can up until 3 o'clock. At 3 o'clock, we'll have the test on chapter 16. Okay? Good deal. We'll see you Thursday. What's that? Oh, by the way, I've forgotten his name. Brian, is he out of earshot? I did get the last lab in, so if you want your last lab, I can give it to you. You want yours, Ricky? Amber? Brian? Okay, there, you weren't out of earshot. I just got the last one. Give them out and then come back. Now you got it.
I'll see you.
Okay, see you Thursday. I'll shut this down for now.